Hello बच्चों, सत श्री अकाल and namaste from my side. So this is a teaser of what content we are going to study in this lecture. Conservation of linear momentum. Impulse. Mind it. Friction is necessary. Newton's first law. Newton's third law of motion. Inertia. So, the lecture of Newton's laws of motion is loading.
So students, this was a teaser, right? As usual, initiative, right? Okay, by us, by entire team, right? For you all. Okay, hope so you liked it. And for this teaser, I will be waiting for, right, your love and all of your comments beneath the video, right? As usual, all the time you are commenting for the lectures and the teasers, right? So this time also I will be waiting. See, I used to read all of those comments, but I never used to respond, but everything is in my, what we can say, I used to monitor each and every part of this, right? So I will be waiting for all of your comments. Okay, so hello bacho, sat sri akal and namaste from my side. How are you all? So this is Indrajeet Singh, your own physics educator, welcoming you all onto the most sensible platform of an edtech, right? The most sensible platform for an aspirants, those who are preparing for JEE and NEET kind of competitive examinations, right? So are you all ready? Okay, so this is a lecture of a champion series, the champion series for you all, right, in a complete English. Okay, so this series, right, so this series was started by the lecture units and measurements, right, and it followed by motion in 1D, and we moved on to the motion in 2D, right, with awesome teasers, right, and now, right, in this today's sessions, right, we are going to see all of those concepts, right, related to the Newton's law of motion, that is NLM. Are you all ready? Are you all ready? So let's begin this session. Okay, as usual, first of all, we are going to have the glimpse, right, of all of those topics that we are going to see in this session. We are going to see, right, Newton's law of motion, Newton's first law, Newton's second law, Newton's third law, right? All of those stuff we are going to see. Apart from this, right, some of the important concepts related to the impulse, right, some of the concepts related to the change in momentum, right, that is impulse, and even for like conservation of linear momentum. After that, we are going to see types of forces, like what is a normal reaction, what is a tension, what is a constraint, what is a pseudo force, what is a friction, right, and right, apart from this, right, the concepts of the spring forces. Okay, so this all of those this sort of concepts we are going to deal with this chapter, and I guarantee, right, I guarantee those who are, right, those who will like stay till end of this lecture, right, obviously they are going to get something, right, because lots of shortcuts we are going to discuss, right, lots of direct question solving approaching, right, we are going to discuss, that will help us, right, okay, in solving the PYQs, and obviously some of the important PYQs we are going to discuss, right? So as usual, as per our tradition, let's begin with the flowchart of this chapter, right? Let's begin with the flowchart of this chapter. So The flowchart starts with, obviously it is Newton's law of motion, it is an LM, right? Hope so this flowchart is helping you a lot, right? And even I will be waiting for all of your comments for this flowcharts also, right? Okay, always shower your love, yaar, because this comments and everything, right? Whatever writing, that acts like a motivation for us, right? Without that, okay, how we are going to apply, how see SPW is box of surprises, right? So how we are going to apply all of those stuff, how? Lots of question marks are there, right? So always show your love into the comments, right, beneath the video, okay, always. So the first part of the NLM, it moves on with the first law, and before first law we are having inertia, right? With inertia we are having the types of inertia, right? And apart from this we are having second law. With second law, right, we are having a right impulse, okay. Second, we are having conservation of linear momentum delta p, that is equal to 0, and lastly third law, right? Okay, so this is the first part, right, of the flow chart. Okay, this is the first right section of the flow chart. Now, okay, apart from this, right, what will be the second part? Right, it is directly moving on to the types of forces that we are going to deal, right? Types of forces, obviously we are going to deal, and among these types of forces, right, so this bifurcation, right, doesn't ends here, right? Okay, the first type of force that we are going to deal is mg weight. Second, that is we are going to deal is a normal reaction, right? Third, right, we are going to deal with the tension. In this tension basis we are going to deal with the Pulley problems, right? Okay, after that we are going to deal constraints, right? Okay, and with this we are going to deal wedge constraints, right? This kind of this stuff we are going to deal with this, right, in this chapter. Okay, after tension, obviously we are going to deal with friction, right? Friction for one body. We are going to see for graph, we are going to see, right, okay, for two bodies, more than one bodies, right, we are going to see. Okay, so this is all of those stuff, right? Mg, normal, tension, friction. After friction we are going to see, we are going to deal with the concepts of the pseudo force, right? And with pseudo force, lastly at the end, spring forces. Okay, and the last bifurcation of this chapter directly moves on, right, to the two most important theories, that is velocity of an object into the banked road, right? And second, velocity is the object into the banked curved road, right? So this is what the entire NLM is. In this, right, obviously this conservation of linear momentum, right, okay, we are going to again see into the next session also, because it is a very important part, right? The conservation of the linear momentum, it is quite helpful, right, in solving the problems of work energy theorem, right? In solving the problems of work energy theorem, this conservation of linear momentum is quite helpful. So we are going to see that stuff again into the next session of work energy and power, right? So guys, this is a complete flow chart, right? This is the complete flow chart of a Newton's law of motion, right, up to the mains level, right? That what kind of the concepts we are going to deal with in this session, and lots of this stuff. If you want to snap, if you want to have a snap, right, I'm going aside and giving you all the 5 seconds on countdown of 5, right? You have to just have a screenshot of it. So it's 5, 4, 3, 2, 1. That's it. Obviously this kind of the stuff you are going to get right into your the notes also, that has been, right, that will be uploaded after this session on the PW app also, and the link will be right beneath like in the description. Okay, so now let's move forward to the most important concept of force. See, why we are dealing with force here, it's the most important thing that you need to understand right before moving on to the in the beginning of the chapter, right? Why this force, right? So if I'm talking about right, the rectilinear motion, that is motion in 1D, right? Second, if I'm talking about, right, the motion in 2D. Okay, these all are parts of the kinematics, right? In this, right, we had a deal with acceleration, right? In this, we had a deal with the acceleration. What kind of a deal? Yes, I am going to analyze the each and every part in each and every motion parameter, but I am not going to deal with the cause of the motion, right? What was the deal, right? Okay, no with the cause of motion, right? Will not have to deal with the cause of the motion, right? So you have seen in all of those examples that we discussed into the previous session in the motion in 1D and 2D, right? It was mentioned acceleration is this, the variations of acceleration is this, but in that case it was not mentioned that what kind of the force, right, it is providing the acceleration, what is the source of acceleration, it was not mentioned. So this is what the difference is, na? In first and second, see, units and measurement, it is a different part. It is completely depending on it is an experimental part of the physics. But okay, as it states, like in measurements. But if I'm talking about 1D and 2D, obviously we didn't deal with the force. We were not interested, right, into the source who was providing the acceleration. In NLM, yes, step to step, the syllabus is designed. Right, in NLM, yes, we are interested in a force, right? We are interested, right, in dealing with a force. Okay, after NLM with force, obviously we are going to deal with the right now in this entire session we are going to deal with the source that is providing the acceleration, how it is providing the acceleration, and how the system state is getting changed with that source, how it is actually connected, right? In the next chapter we are going to deal, right, with the energies and the work done with this force, step to step, right? Okay, this is how it is designed. And after that we are going to deal with the rotational part, that is torque and linear angular momentum and all of those stuff. Okay, so this was the most important note from my side, right? Till now we haven't dealt with the cause, but in this session, right, we are going to deal with the cause. We are going to deal with the cause. Now, let's move on, right? What is a force? Obviously, this is a cause of a motion. Sometimes it will be the net force, right? Lots of things are there. But how we can, right, okay, generalize the definition. If someone asks me what is force, I can't say, right? If someone asks me what is force? In our day-to-day life, we are completely aware of. But if you want to write that into the technical terms, okay, lots of definitions are there into the thousands of resources. But what will be the short and sweet definition of the force, right? So I might define it as a push or pull. Any kind of a push or pull that can change the state of the object, right, that can change the shape of the body. Okay, lots of blah 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 things are there. Generally, if I want to define, force is nothing else but the push or pull, right? Let's have the example of it, right? Let's have the example of it. Suppose if I'm having mobile in my hand, right? Okay, what factor forces, right, my hand, right, to hold this mobile? Can I say this is a pull? Can I say this is a push? The best example of a pull or push is whenever you are entering in restaurant, there is always a tag, okay, on the edge of the door near the handle, right? There is always a tag. Push, pull. Push, it means we are moving like this way, we are applying the force like this way. right? Okay, we are applying, I can't say as a force, we are applying an effort like this way into the forward direction. Pull, it means we are like applying the effort, right, like this way. Okay, so that's a push or a pull, the basic definition of the force, right? The most basic definition. The push or pull that can change, right, the state of the object, sorry, state of an object, right? Apart from the state of the object, even sometimes it can change the shape of an object, right? It can sometimes even change the, okay, the push or pull that changes the state of an object or shape. Apart from this, lots of definitions are given, right? So this is an actual definition of the force. Right, now let's move on to the most important part of Newton's first law. Now, before moving on to the Newton's first law, you all are aware of the statement of the statement of it, right? But before moving on to that, it is important to understand what actually inertia is, right? What actually inertia is. What is inertia, right? So till now, those who are watching this lecture, right, okay, this will be the most interesting part of this lecture, because this thing I'm going to show you all with the one word in Hindi, that is known as, I will represent this thing, right, in one word. If I want to represent, if I want to define this thing in one word, and obviously in Hindi language, and it will be taklif. In Hindi, it is taklif, problem, issue, thought, negative thought, taklif, a feeling, right? Now, what kind of taklif? What kind of an issue that body is having? Obviously, if I'm talking about the inertia and I'm in summarized form, if I'm defining it as a taklif, right, if in summarized form, if I'm defining it as a taklif, then obviously it might be related to some entity. And in motion, entity means, right, a object, right? Entity means, right, we are talking about our object. Okay, so taklif, what kind of a taklif inertia means, right? For that, let us take a very simple example in front. It's 6 a.m. as you've seen in teaser. It's 6 a.m. in the morning, right? It's a winter morning. Suddenly, if someone, right, pushes me, right, or pours a bucket of water, right, because it's what we can say, a flight time and we need to move on, right? It's an early morning flight, and obviously winter mornings are quite helpful for us to gain, right, to lose some momentum in life, right? Okay, winter mornings are quite helpful, right, to lose all of the momentums, all of those thought processing that we are having in our mind. Either it is positive, it is negative, we are not aware of, right? No, winter morning we just want to enjoy, right? This side, one hand this side, one hand this side, right, and like this way. So at that moment of the time, if someone enforces us to, hey Indrajeet, come on, wake up, right, it's time to move, we are having just 3 hours left to our morning flight. So at that time, right, we were having a feeling, a thought. In Hindi, it is known as taklif, right? In Hindi, right, it is known as taklif, right? What kind of the taklif? I don't want to wake up, but someone is forcing me to do so. I want to be in my old state, but someone is forcing me to change my state. And resistance to change, right, in a state is a property of an object, is inertia. That's why I define inertia as taklif, right? Okay, now what will be the exact definition? See, you can see the truck is in its original state. Basically, we can say either the state of rest or state of motion, right? You can see into the visualization, the truck is in its original state, but suddenly due to the presence of an obstacle, right, this obstacle right, forces trucks to stop. So in that case, this truck is having a problem in changing its state, right? This truck is having a taklif in changing its state, right? So that taklif, it is known as what? Inertia. The object never wants to change its state, but as because of external force it happens, and he must, right, I can't say he must, but he have to do it, right? It's like a pressure of an external force. I have to do it, right? It is an pressure, right, that I have to do it. Okay, so what will be the inertia? That is taklif. How I am going to define it? The resistance of a body to a change. Resistance of a body to a change. What kind of a change? Either it can be the change of state, right? Either it can be the change of direction, either it can be the change of a motion, right? Resistance to what? Taklif to what? Lots of types of taklifs are there, na? Right? For inertia, lots of types of taklifs are there, right? Okay, I like momos, that is my problem. But when I don't get momos, there is a bigger problem, right? When there is a lockdown, I'm not going to move on, like I'm not able to move on, right, to the XYZ outlet of momos, right? Then it's a bigger problem, right? So how problem is, right? Okay, this might be what we can say the boon for someone, and this can be the curse for someone. Right? Boon for someone, those who are not liking momos like me, right? Okay, I never used to eat all of those steamed momos. No, it's like a boon for me. So those who are fond of it, right, they will find each and every possibility, right, to attain that thing. Okay, to attain that motion, because they don't want to be into the older state without momos, right? So that taklif, that problem they are facing, that is the property of an object, that is, right, okay, the resistance of a body to its change, right, that is inertia. Okay, that actual is inertia. Okay, it is the most important part for the Newton's law of motion. Now inertia, it means in three terms, three classification: inertia at rest, inertia in motion, inertia in direction. Inertia at rest, inertia in motion, inertia in direction, right? Three kind of the inertia. In summarized form, inertia is a kind of a resistance to a change. As I said, lots of technical definitions are there in lots of resources, but whatever I'm representing in front of you all, right, whatever I'm representing in front of you all, it's all about, right, the things should go smoothly. Physics should be understood by you all, right, quite smoothly. That's why, right, I'm keeping these things in front of you all. Okay, so rest, motion, direction. Rest, resistance to change in state of rest. You can see into the visualization, it's a very simple experiment that, okay, thousands of students, like maximum number of the students, they have, right, done into the life. Suppose I'm having the glass of water, right, on that I place a piece of a cardboard, on that, right, I kept a coin. Suddenly, see, what is the initial state of an object? That is, I'm talking about a coin. right? It is at rest. Okay, it is at rest. But suddenly, right, if I'm just pushing, right, sorry, pulling the cardboard, right, this is a glass of water kept, the cardboard piece of the cardboard is kept on it, and then on that, right, we have placed a coin. Suppose if I'm moving this apart, right, what will happen, right? Coin will obviously, right, fall into the water. But here the object wants to be in older state, the state of rest, right? Object want to be in its older state of rest, but the external force is, right, okay, external force is, right, is creating a kind of a pressure. It technically, I'm not talking about a pressure, no, it forces, the external force, right, it forces an object to change its state. When I will move this piece of cardboard apart, the coin is going to fall. So initially the state was, the object was at rest. After some amount of the time, right, it is in motion, right? So this state change, the resistance to this kind of a state change is inertia at rest. So when I define inertia, I define it as a taklif, but basically there are three kind of taklifs, right? Taklif in changing the state of rest, right? Taklif in changing the state of motion, and taklif in changing the state of direction. The next is motion, right? What kind of a taklif, right? Resistance to change in motion of an object. Resistance to change in, right, resistance to, right, change in, right, motion of an object, the state of, right, resistance to, right, change in state of the motion of the object. The best example of the inertia in motion, right? Best example, public transport, right? Many students might have traveled into the public transport, right? And some might have traveled into the your own transportation vehicles also, right? Into the own transportation vehicles also. Obviously, it is an obvious thing, right? Now what happens, suppose you are moving into the public transport, suddenly the driver applies the brake, what will happen, right? Analysis of this thing will give you the definition of inertia in motion. Analysis of this thing will give you the definition of inertia in motion. Now what will happen initially, right, when bus was having, let us take an example, bus is moving with a constant velocity, right? Bus is moving with the constant velocity, right? Then what is a habit for an object? I am in a I am in a state of motion. I am in state of motion. I want to be in state of motion. I don't want to change my state. I want to be in state, right? I want to be in my older state. But suddenly if any animal or any like if someone crosses the road and driver needs to apply the brake, then what will happen? I will be, right, the body will be automatically pushed like this way, right? Why this happened, right? Why this happened? Because the your lower part was of the body was completely at the, right, on a seat, right? Okay, before, right, brakes were applied, your body was in a state of a motion with a bus. But suddenly when, right, driver applied the brakes, right, your body wants to be in original state, in the state of motion, right? He don't want to change a state. He want to be in older state, but external force, as because of external force he has to do it, right? So for that reason, right, when brakes are applied for very small amount of the time, right, the body, right, will be in its original state, and after that we used to, right, hold the front seat like that, and we're going to say ourselves, we are going to say, we used to say ourselves, right? So what is that? I want to be in older state. Body was right, having its older state. Suddenly it moved on. Okay, I was moving like this way, brakes were applied, but I am in its original state like this way. So for that reason, right, we are having this kind of a effect, right? This kind of the right push we are feeling, right, into the upward direction, into the front direction, or into the backward direction, right? Okay, so that is nothing else. I want to be in my older state, right? That's a resistance of the body that don't want, that is this, that is, okay, it doesn't want to change its state, and that's the property of an object that shows in taklif, that is inertia in motion. Third, resistance in change of its direction. Resistance of change in its direction. A very simple example of our day-to-day life, right, to understand the inertia in, right, a direction. Okay, the third classification. Suppose if I'm right, if your dad is driving the car, right, and you are seating right to the back. Suddenly, if your dad, right, is taking the left turn, right, okay, kindly be careful here, right, it is a very simple example to understand, right? Okay, see, you're moving forward. What is the old state? What is your old direction in moving forward? Right, okay, the object is in a state, right, of a motion, and he is moving forward. What is its direction? Right, its direction that he is moving forward. But suddenly what happened, right, the external force, right, okay, creates an impact, so that object should change its direction. I'm moving forward, that's my older state, but suddenly if my dad took a left turn, right, my body is still for the fraction of time, right, it's still in its original state. So that's why we feel the effect of like moving towards the right. Whenever the vehicle took a turn, right, whenever the vehicle, right, okay, is turned towards left, body is pushed towards right, right? If we are having kind of a feel that we are, right, not a feel, actually it happens, right, we are, right, pushed towards the right side. If the object is moving, actually we are not moving towards right, no, right, okay, object is moving towards left, we are having, right, we are having the direction of motion into the right, okay, we are heading, right, into the forward direction only, but when it takes a left, the body tends to move its original state. Left, the body wants to be in original state. This is a new direction, the body wants to be in original direction, right? The resistance to the change in this direction, right, okay, that is inertia. So it's not when it, right, car is turned left, then we are, right, moving towards the right, or when it is turned right, we are moving towards the left. No, it's not like that, right? We are moving forward only, right? Our old direction is to move forward, right? We are moving in that only, but actually the car, right, took a left turn, so we are having a kind of feeling that we are moving towards right. No, actually it is not a right, it is moving, like it is your older direction only, right? So this is what the classification of the, right, three inertias. After that, it's a very simple right, example of the first law, right? It's a very simple example of the, right, first law, right? It happens with us, right, into a day-to-day life, but when it happens, right, into the winter mornings, then it is quite, right, it is disastrous, right? Okay, you can see granny is, right, pouring the water, right, to his child, to her child, I'm sorry, to her child, right, that it's a morning and you need to move out for your work, it's a time to wake up. So that shows the example of the Newton's first law, right? That clearly demonstrates the Newton's first law. Now, what actual the statement is and what it states? It states object at rest will be at rest. In motion will be in, right? Okay, if it is at rest, it is at rest. If it is in motion, it is in motion until and unless external force acts on it, right? Until and unless, right, external force acts on it. Now, what kind of the external force here? The granny, she is pouring the water, right? Here, the splash of the water is acting like an external force, right? Okay, this object want to be in its older state, right? But external force, the splash of water, right, changes its state. So that is what written, that is what mentioned, right? Okay, that is what mentioned here, right? Okay, okay, object at the rest will be at rest. Okay, in motion will be in motion, right, until and unless external force acts on it, right? Okay, until and unless external force acts on it, right? So this is what the simple example, right, of the Newton's first law of motion, right? This is a statement. Okay, now let's move forward to the Newton's second law. Before moving on to the concepts of the second law, let's have the statement for it, right? Let's have the, see why we are moving, right? See, we are not moving fast, right, in Newton's law, but we have to do it because lots of time we need to okay, lots of the like maximum amount of the time, right, that will be consumed in explaining the tensions and Pulley based problems in frictions and all of those stuff. So that's why, right, immediately we are moving forward to this part, right? Okay, the second law of motion, as I said, object want to be in its older state, but he has to change his state as because of the presence of the external force, right? As of the presence of the external force. But it means that if state is getting changed, velocity is getting changed, acceleration is getting changed. Question mark. Acceleration is getting changed or not, that is a different thing. But if the state is getting changed, obviously, right, the velocity is going to change. So what this right second law states, right, now we are completely aware of what actual the linear momentum is. We are completely aware of what actual the linear momentum is. Now what this second law states, the time rate of change in momentum, the time rate of change, right, the time rate of change in, right, momentum of a particle, right, is directly proportional to, I'm extremely sorry now what it's happening today, yaar. Okay, okay, the time rate of change in momentum, right, the time rate of change in momentum is directly proportional to external force applied. The time rate of change in momentum is directly proportional to external force applied. Right. Okay. So this is a statement of the Newton's second law. It means that Fp is directly proportional to, right, time rate of change of momentum. For a very small change, right, for a very small change, we can define this equation as right, the external force is directly proportional to dp by dt, right, where dp by dt is a small rate of change of momentum, small time rate of change of momentum, right, the small time rate of change of momentum. You can see in this visualization, right, you can see in this visualization, this is the best example, right, the external force is applied, right, by this person using this hammer, right, okay. You can see there is an object that is present at the bottom of the system, right, you can see that red one, right. See, when external force is applied initially, right, you can just check it out. Initially, you can see this visualization. Initially, right, it was at rest. Initial velocity was 0, right. As I said in our previous lectures, we were not going to deal with the cause of the motion, but see, right, in the previous case, if I'm talking about the first, second and third chapter, right, the motion in 1D and 2D, right, so we were having the statement like object is thrown, right. In this right, in this chapter, there is a difference. As I said before, external force is applied and object is moving. So this is what we are dealing with, the cause. This is what, right, we are dealing with the cause. Initially, right, the velocity is 0. Suddenly, right, F external, right, is applied. Suddenly the external force is, right, applied. Now what will happen? If external force is applied, then what will happen? Right, okay, external force is applied, then what will happen? Right, okay, there will be change in the state of an object, right, okay, okay, object will gain some velocity and that will be v, okay. So for that reason the object is moving into the upward direction. So as because of the external force, right, velocity is changing from 0 to some positive values or negative values, and as because of that there is a change in momentum with respect to time, right, okay, there is a change in momentum with respect to time. So with an external force, right, when external force is applied, it is directly proportional, right, to the time of rate of change of momentum. This is what the Newton's second law is. This is what the statement of Newton's second law. Now, with the Newton's second law, two most important things, right, we are going to deal. First, what is the change in momentum, whether it is constant or not. Right? Either we are talking about the system or an object. It means in another sense, we are going to deal with the two more important stuff. The first one, that is impulse, and second one, that is the conservation of the linear momentum. The first one, that is impulse, and second one, that is conservation of linear momentum, right? So the visualization is there in front. Let's see this. The most important part is, this is not how the external force is acting. The most important part for this concept is how velocity is getting changed, and with respect to that, how momentum is getting changed. See, first of all, I want to tell you all, right, some most important information regarding the momentum. See, momentum is what? A vector quantity, right? Momentum is what? A vector quantity, right? It means, suppose if I'm writing the momentum is changing, it means what? Its magnitude is also changing, its direction is also changing. Suppose if I'm writing, there is only change in, see, magnitude is constant, right, and direction is constant, sorry, direction is changing, right? So in another sense, if this is also happening now, then also the momentum is getting changed. The third part, for momentum to be constant, right, both magnitude and direction, right, okay, they both need to be constant. Okay, then I can say the momentum is, right, okay, constant. So in this, right, we are going to deal with the second and third part. Okay, how momentum is getting changed, whether the momentum of the system is getting changed, whether the momentum of the object is getting changed, how linear momentum is conserved, how momentum of the initial and final momentum of the system is getting right equal. All of this stuff we are going to discuss. But in this case, the most important information was how, right, we can define momentum. Momentum actually is a vector quantity, right? Mathematically it is represented as P is equal to mv. Technically, if we want to define the momentum, then the amount of a motion contained in system is defined as momentum, right? Amount of a motion that is contained in system, that is defined as momentum, right? So this was the definition of the, right? Now this is changing is because of an external force, right? Okay, now how it happens, how we can define impulse, let's see. Let's have an example. Suppose this is an object of mass m. Initially it is having u speed. Suppose, right, okay, one force is acting in the direction of the motion of an object that will increase its velocity after some time t. Right, particle is at this position and it is attaining the new velocity v. So from u to v, right, the velocity get changed, right, okay, and with the change in velocity we felt, right, yes, the momentum is getting changed. So here can I say, according to the Newton's second law, the ab force is directly proportional to change in momentum with respect to time. Removing the proportionality sign, right, this is a proportionality constant, that is F is equal to K del P by del T. Suppose if K is equal to 1, if we are taking K is equivalent to 1, right, so F is equal to del P by del T. Here del P, that is equal to F delta T, right, that is equivalent to change, right, in momentum, that is equivalent to impulse. You've seen this into the DC movies, right? You have seen this visualization into the DC movies. Suddenly I'm at rest, right, and in just a fraction of a second, just a fraction part of a second, I'm getting the, right, I'm attaining the speed of light. In a fractional part of the second, I'm attaining the speed of light. This is what about, huh? This is what this is a power this is superhero contains, right? Anything, right? Okay, initially it was at rest, suddenly it started moving with the, right, and the very fractional part of the second it started moving at the speed of light, right? So there is a high change in momentum, right? It means there is a possibility of acting an external force onto it, right? So here the change in momentum is nothing else but an impulse. The change in momentum is nothing else an impulse. So I must define it as a change in momentum. The simple and quite right, what you can say, the definition into the quite summarized form. Change in momentum, that is impulse, right? This is the formula, right? Sometimes it is F delta T, sometimes it is, right, if this motion parameters are also given, right, and actually it is written into the vector form, that change in momentum, that is equal to F, right, delta T, okay, and sometimes it is, right, if you want to represent this terms, right, then V final vector minus V initial vector. Actually it is everything, right, it is a vector quantity, then it should be represented into the vectors, right? Okay, but I wrote the magnitude part also, and I considered the direction also, right? The two equations are in front of you all. So that is what impulse is, right? Now let's move on, right, to the most important, right, okay, some sums related to the impulse. Okay, see, first of all, as I said, according to the Newton's second law, right, F is equal to del P by del T. right? Okay, so first most important note, if it is, right, momentum versus time graph, right? If it is momentum versus time graph, then slope will give the force. Slope will be equivalent to tan theta, that will be equivalent to dp by dt, right? Or that will be equivalent to del p by del t if the change is quite high. This will give you the force, right? The second most important right note that I want to give you all, right? If it is, right, force versus time graph. See, everything is completely based on Newton's second law only. Everything is based on Newton's second law only. If it is momentum versus time graph, then we are having slope as time rate of change of momentum, and that is equivalent to the external force, right? But if it is F versus T graph, right? If it is F versus T graph, right? So I must say the area that will be equivalent to F delta T, that will be equivalent to impulse, right? And that will be equivalent to change, right, in momentum. Right? If you want to have a snap of this note, this is a most important note, right? If you want to have a snap of it, just have it, right? If you want to have a snap of it, just have it, right? I'm moving aside, right? And on the countdown of 5 seconds, right? Okay, you have to do so. It's 5, 4, 3, 2, 1. That's it. Okay, see. Now, one question we are having in front. Right, this has been asked into the 2014 paper, right? It is a PYQ. Okay, see, the force acting on the particle of mass m is indicated by, say, it's force versus time graph, right? It's force in the Newton, right, and time into the second. As usual, I say, if it is momentum versus time graph, then slopes gives force. If it is force versus time graph, right, the area gives change in momentum, right, or you can say impulse. Right, so the change in momentum of the particle over 0 to 8 seconds in between, right here I'm writing out, in between t is equal to 0, right, to t is equal to 8 seconds, right? T is equal to 0 to t is equal to 8 seconds, we need to calculate. See, any time interval can be asked into the question. Suppose, right, in question I'm changing a bit of it. Suppose the graph is plotted between time interval 0 to 8 seconds, but I'm asking what will be the change in momentum 0 to 4. Now in this question, we are completely aware that it is a force versus time graph, and we need to calculate, right, the change in momentum, or that is impulse. So it means that we need to deal with the area. According to the Newton's second law, right, F delta T, that will be equivalent to delta P. So F delta T, that will be area under FT graph, right, and that will be going to be change in momentum. Now here the important question is, right, what area we need to consider. Okay, so in the time interval, right, whatever the time interval that is mentioned into the question, that much area you need to cover. And in that area, if any parameter is positive, it's positive. It is negative, it's negative. It's not like a motion, right, in 1D. Right, so this is the entire area we need to cover. Can I write this as A1? Can I write this as A2? Can I write this as A3? Right, so the total change in momentum, that is equal to area under, right, FT graph. Right, so can I say the total area between 0 to 8 seconds of time interval, that is A1 plus A2 plus of A3. Right, A1 is a triangle, so can I say it is half base. Base is of 2, altitude is of 6, right, plus this one is what we can say a rectangle, base is of 2 and height is of -3, so it is -3 into 2, length into breadth, plus that this is also the rectangle, base is of 4 and height is of 3, right, so 4 into 3. So this 2 is going to cancel, 6 minus 6 plus 12, right? The total change in momentum, that is equal to 12 kg meter per second, right? And that is the perfect answer for this specific question, right? Okay, that is the perfect answer, right, for the specific question. Okay, that is a perfect answer for this specific question, right? Okay, so can I say it's right? Okay, 12, okay, 12 Newton seconds, right? That is a perfect answer, or 12 kg meter per second. Okay, so this is how area is calculated. Now let's move on to the next question. Right, so in this, what will be the impulse between 0 to 8 second? Here I want to write it out. Impulse, right, that is equal to change in momentum, right, in between t is equal to 0 to t is equal to 8 seconds, right? So impulse, that is equivalent to what? 12 kg, right, change in momentum, that is 12 kg meter per second, right? Now this was right, we dealt with the magnitude. Now we are going to see right, the directions of it. Okay, this question is quite important, has been asked in 2000 PYQ, right? A body of mass 3 kg, body of mass 3 kg hits a wall at an angle of 60 degree and returns, right, the same. Impacted time was t is equal to 0.2 second, 0.2. Now what is external force exerted on the wall? See, it's like that. See, ball is coming, right? Okay, now you all might be having a question in your mind. Sir, only the direction is getting changed, the velocity, the magnitude of the velocity of the particle is constant. So as I said into the beginning of this, right, concept, okay, that for an impulse, right, it is equivalent to change in momentum. The change in momentum is in two ways. First, either magnitude is changing, either direction is changing, or both are changing, right? So three possibilities are there. So here, if it is a direction is getting changed, it is a change because it's a vector quantity. With a change in direction, yes, the momentum is getting changed, right, in spite of right, magnitude being constant. Okay, so here how we are going to deal with this stuff? Let's draw this figure, right? Okay, see, okay, see, suppose let us take an example, right? It's coming like this way, right? For t is equal to 0.2 second, for t is equal to 0.2 seconds, obviously, right, t is equal to 0.2 seconds, right, the ball is having impact with the wall. Yes, I can understand it is a very small amount of the time, right, but for this time interval, right, it is going to create an impact. It is going to impart a force on the wall, right, and that we are going to calculate by means of the Newton's second law or the equation of change in momentum, right? So this direction, right, they have given, okay, 60 degrees with respect to vertical. So can I break this component, right? Okay, this will be 10 sine of 60 degree because this is a 60 degree, right, and this will be, right, 10 cos of 60 degree, right, and this will be the 60 degree. Okay, now after the impact time, the ball is returning like this way, right? Okay, with the same speed, 10 meter per second, and obviously the direction is being same, right? Now, okay, the direction, right, of the momentum got changed. As why? Because the direction of the velocity got changed. So here, right, the new parameters will be like this way, right? I'm sorry, the new parameters, right, will be like this way, right? This will be 10 sine 60, right, and this will be 10 cos 60. See, you can see the vertical component of the velocity, right, it is not getting changed. Here also it is 10 cos 60 and the direction is in, like, it's acting in downward direction. Here also it is 10 cos 60 and it is acting in downward direction. It means that whatever the impact we are getting, it is just because of the horizontal component of the velocity. So here I want to write it down, right? The vertical component of velocity is not getting changed. The vertical component of the velocity is not getting changed, right? Vertical component is not getting changed. It means that, right, impact is only as of horizontal component, right? And this horizontal component is only going to, right, okay, this will be the responsible for change in momentum of the particle, right? And what will be the change in momentum into the vector form? That is m delta v, right? Okay, m delta v. Okay, so in another sense, if we need to calculate this change in momentum, right? Okay, so we can write it down into the vector form as what will be the mass, right? Okay, the mass is 3 kg. So can I say it is 3, right? Change in velocity. See, initially, if we are considering the sign conventions, it's final minus initial, right? It's final minus initial, but in another sense, it's 2 sine of 60 into negative I direction. And if I'm talking about the magnitude of this, right, then it will be is 3 into 2 into root 3 by 2 into 10, right? So delta B in terms of magnitude, it is 2 is gonna cancel 3, 30 root 3. Okay. Now we need to calculate the force. I'm extremely sorry for that. So force will be change in magnitude of momentum by change in time. So this will be equivalent to 150 root 3 Newton. I'm extremely sorry, right? This will be equivalent to 150 root 3 Newton. Okay, so this is how these things are calculated, and A is the perfect answer for this, right? A is the perfect answer for this. Okay, now let's move on, right, to the next part, that is conservation of linear momentum. Newton's second law, right? We already did that part. Right now, let's move on to we saw that if change in momentum is happening, right, then we are having an impulse, right? Now again, I want to tell you right now, I want to classify the classification. If I'm talking about an individual, that is object, or if I'm talking about a system, right? If I'm talking about an individual, that is an object, or I'm talking about a system. If I'm talking about an object, always the velocity is getting changed. Always we are having delta B is not constant. If I'm talking about if x in presence of an external force, right, or internal, whatever it should be, right? Okay, but if I'm talking about an object, right, I can't say the momentum is constant. Initially, whatever value it was, right, finally it is not sure that it will remain same. But for a system, if external force is 0, yes, for a system the change in momentum is 0, and that's what the conservation of linear momentum is. So before moving on to that topic, I want to really differentiate, right, the two thoughts in front. First, whenever you are thinking of an individual object, we can't conserve the linear momentum, because the linear momentum is always conserved for system, and that also in presence of an external force, right? See how. Let us take a very simple example to understand this. Suppose this is mass m1 and initially it is moving with mass velocity u1. This is mass m2 and it is moving with velocity u2. Now they are colliding, right? So this is before. After what it's happening, right? Okay, this is m1, this is m2. The velocity is getting changed to v1, right? Okay, velocity of the, so if I'm talking about an individual particle, the velocity is getting changed from u1 to v1. Yes, there is a presence, there is a change in momentum, right? Impulse is imparted, right? If I'm talking about individual asset m2, right? Okay, the velocity is getting changed from u2 to v2. Obviously, the impulse is imparted. But if I'm talking about the whole system, right? If I'm talking about the whole system, right? And if external force is 0, then the linear momentum of system is conserved. So whenever you are dealing with the whenever you are dealing with the conservation of linear momentum, always consider the system. Okay, at least two interacting particles should be present. Right, at least, see, you can see in this visualization, right now two interacting particles are there, right? Okay, whatever what we can say, the force, the impulse they are imparting, right? Okay, see, momentum is getting changed for the individual particle, but finally it is getting balanced if entire system is considered, right? Finally it is getting balanced if entire system is considered, right? Finally it is getting balanced. So in another sense, whenever you are dealing in summarized form, whenever you are dealing with the conservation of linear momentum, right, whenever, right, you have to consider the entire system. If you are considering the individual particle and velocity is getting changed, it means impulse is imparted. For system, change in momentum is always 0. Right, so can I write change in momentum into the vector form is 0? It means that initial momentum, right, that will be equivalent to final momentum. So it will be m1 u1 plus dot dot dot. For n particles it is mn un. Final momentum, right, that is m1 v1, right, plus dot 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 plus mn vn. Right, this is what the conservation of linear momentum states. Right, this is what the equation of conservation of linear momentum is. Right, okay, just two things into the mind. Entire system, net external force should be 0. Entire system, net external force should be 0. See, in this case we were talking about an individual body, right? That's why we considered an impulse, right? That direction is getting changed, right, for a body. It means, right, if direction is getting changed or something, okay, there is some change in momentum, and obviously the impulse is imparted. In this also, right, see, for an individual particle, force versus time graph is given. It means for an individual particle there is an impulse. For system, if external force is 0, right, momentum is conserved. Let's have an example for it. In NEET 2019, Odisha, right, in NEET 2019, right, this question has been asked. Object is an object flying in air with the velocity suddenly break into the two bases. See, this is object. Let us take an example. This is of mass m, right? It is moving on with an initial velocity vector u that is given 20I plus 25j, right, minus 12k. This is a velocity vector, right? This is the velocity vector. Now suddenly it breaks into the two parts whose masses are in ratio of, right, okay, masses are in ratio of, right, here it is written masses m1, it is breaked into the two parts, so masses are in ratio of 1:5. Right. So can I say, suppose this is it is getting breaked into the two parts, so can I say m1 that is equal to m by 6, right, m2 that is equal to 5m by 6. Its ratio is like this way. The smaller mass, right, which one is a smaller mass? right? M by 6 is a smaller one, right? Or 5m by 6 is a smaller one. Obviously the m by 6 is going to be the smaller one. It flies up with the velocity 100i 35j, right? The v1 is, right, 100 of I plus 35 of j plus 8 of k, right? This will be the v1 velocity. Then what will be the velocity, right, of the larger piece? Okay, this is the situation in front. What we need to calculate, see, external force on the system is 0. External force on the system is completely 0, right? External force on the system is 0. It means that for entire, I'm not talking about an individual particle, for entire system momentum is conserved. So it means initial momentum of the system that is equivalent to final momentum. Initial momentum of the system that is equivalent to its final momentum, right? So can I say here, it's a very simple thing. Can I say here, initially mass was m, it was moving with velocity u. Finally mass was m1, it was moving with velocity v1. Another mass was m2, it was moving with velocity v2. We need to calculate the value of v2. M, right? Okay. Velocity is 20i 25j minus 12k. So can I write it as m 20i plus 25j, right, minus 12k. This is the value of the u we have replaced. M1 is m by 6 and it is moving with, see, it is m by 6, right, and it is moving with, okay, 100i 35j 8k. 100i 35j 8k plus m2 v2 vector. I am replacing the m2, right? Okay, I am replacing the m2 as right 5m by 6, right? Okay, so here first of all I want to tell you all, this m will be get cancelled, right? And this final equation we can write it as 120 of I plus 150 of j, because 6, this we are multiplying to the opposite side, okay, 72 of k, right, that will be equivalent to 100 of I, right, plus 35 of j plus 8 of k plus 5 v2, right? Now final equation is 120 minus 100 of I plus 150, right, minus 35 of j. This is what now, 150 minus 35 minus 72, right, minus 8, minus 72 minus 8 of k. This will be equivalent to 5 of v2 vector. So this is the what velocity of the second particle we need to calculate, right? The velocity of the second particle we need to calculate. So 5 v2, that will be equivalent to, it's 20 of I plus 150 minus 35. So it's 115 of j minus 80 of k. Let's divide it by 5. So it's 20 by 5 of I plus 115 by 5 of j minus 80 by 5 of k, right? So what will be the velocity of the second particle? The velocity of the second particle will be, right, 4 of I. Okay, we are having, right, 5 2s are 23 into 5, that will be equivalent to 115 plus 23 of j, right, 5 1s are 5 and 36 16, right, minus 16 of k. This will be the velocity of the second particle. 4i plus 23j minus 16k. Right. So this is how, this is a step-to-step procedure, right, to apply the conservation of the linear momentum. Right. Okay, it is given now, right, mass is divided into the ratio of 1:5. Mass is divided into the ratio of 1:5. So it's 20I, right? Okay. Initially the particle was having 20I, suddenly see it broke as because of the internal forces. Some students might be having, right, a problem, having a doubt, right? Okay, if it got braked, right, it means there is a presence of external force. No, see, whatever the explosions it is happening here, na, right, as because of that this particle is getting braked into the two parts, into the mass ratio of 1:5. It means that there is a presence of whatever the explosion that is going on, it is just because of the internal forces, right? Okay, now let's move on to the another sub, right, of the changing momentum. Now there is a famous question of recoil velocity of gun. Suppose there is a gun of 2 kg, mass of gun of 2 kg, right? Okay, mass of bullet that is equivalent to 100 gram, 0.1 kg. Initially the system is at rest. First point, initially the system is at rest. Suppose if bullet is fired with the velocity of 100 meter per second, what will be the recoil velocity of the gun? Right, this is what the situation is, the very famous example of the recoil velocity of the gun, right? See here, again I want to tell you all, whatever it is happening, right, if I'm talking about the system, right, now what is included into the system? Gun and bullet, right? So it means for system the external force is completely zero, right? If I'm talking again and again, why I'm mentioning the system, right, why I'm differentiating the system and the particle, because, right, you are always going to confuse in between that. So external force is zero on the system, it simple means momentum is getting, right, constants. This will be for system. So initially mass of bullet, right, at rest, mass of gun at rest, finally mass of bullet, right, it was moving with the velocity of 100. Let us take an example. The gun is moving into the, see, if the bullet is fired into this forward direction, then we will have the recoil velocity into the backward direction, right? Okay, then and then only the momentum will get conserved. This is what action is, plus mass of gun into velocity of gun, right? So can I say mass of bullet into velocity of bullet into negative, that is mass of gun into velocity of gun. So what will be the recoil velocity of the gun? That is negative mass of bullet. Mass of bullet is 0.1, velocity of bullet into 100. Okay, mass of the gun is 2 kg, right? Okay, mass of the gun is 2 kg. So it means that velocity of the gun, that will be equivalent to minus 10 by 2, that is negative of 5 meter per second. Negative in another sense, if I want to represent this into the vector form, that is negative of 5I meter per second if, right, velocity of the bullet is 100I meter per second. So this negative part indicates the direction, right? We are having, suppose I am firing, you have seen into the teaser of the bullet, na, like we are doing like this way, right? I holded this machine gun like this and I'm firing, so we are having recoil velocity like this way, right? If bullet is in the forward direction, then we are having the recoil velocity in the backward direction. Okay, so this question is for homework. Right, you can answer this question beneath the video, right, as usual. And here, right, the Newton's second law of motion ends, right? Newton's third law, the action and reaction, right, this everyone is aware of, right? We are not going to discuss and we are not going to, right, deal with this, and you're not going to consume much amount of the time, right? Action and reaction, equal in magnitude and opposite in direction. Right? Action and reaction are equal in magnitude and opposite in direction. You can see in visualization, right? Something is stored. Action, reaction, right? Rocket propulsion is the best example of the Newton's third law. So this is what is, we are not going to deal detachment amount of the time in this case. Now, the most important part of this chapter is types of forces. Basically, 6 types of forces we are going to deal with this. The first, this is weight. Second, it is a normal reaction, right? Okay. The third one, we are going to deal with the tension, right? The fourth one, we are going to deal with the friction, right? The next, we are going to deal with the pseudo force, right? And finally, we are going to deal with the spring forces. The spring forces and the conservation of the linear momentum will come right into the next chapter also. It's not a big deal, but right, we'll have a glimpse of it, right? We will have a glimpse of it, right? So this much amount of the forces we are going to deal, right? Okay. Now, what will be the equilibrium of a forces? What is this equilibrium? Very simple. I am talking about the conditions of the translational equilibrium. A very simple thing, equilibrium in the free body diagram, because this thing we are going to deal maximum into the next part of this session. Translational equilibrium, if acceleration, the net acceleration along the y direction is 0, it means the summation of all forces along the y direction is 0. If the net acceleration along the x direction is 0, it means that summation of all forces along the x direction is 0. Let us take an example to understand this. Let us take an example. Suppose, right, this is mass m. One force is in this direction, F1. Second force is in this direction, F2. Third is in this direction, F3, and this one is in fourth direction. If net acceleration right along the y direction is 0, it means summation of all y forces are 0. It means F1 will be equivalent to F2. Forces always occur in pair, right? Forces always occur in pair. F1 is equivalent to F2, right? Second, if the net acceleration along the x direction is 0, right? It means all the forces, the summation of all forces along x will be 0, right? F3, that will be equivalent to F4, right? This is what the equilibrium condition is, right? It directly correlates, right? Okay, to the Newton's second law also. But this thing, all of this thing we are going to see into the right the next part of the lecture. And next about the free FBD, right? What FBD is? It is a free body diagram. Now what actually the free body diagram is, depicts the all forces, right, acting on a particle. All forces that are acting on a particle, right? Particle. Okay, this is also you all are aware of. Now let's move on to the first most important force. Mg is nothing, it's weight, you all are aware of, right? We are directly moving on to the sums of the normal reaction and what actually the normal reaction is, right? What actually the normal reaction is. So till now we moved on, right, to the concepts of like Newton's first law, second law. We moved on, we saw the conservation of linear momentum, the concepts of impulse and the respective direction. After we saw the FBDs and the equilibrium of the forces, right? Even we saw the classification of the forces also. Now it's time to move on into the detailed approach of all type of the forces, right? Among them, right, the first one is the normal reaction. Now, what actually the normal reaction is, how it acts, right? Lots of things we are going to discuss in this session, right? After that, we will move on to the tensions and types of densities and everything. Now, what is a normal reaction? Now, the definition states the perpendicular component of the force right that acts between two contact surfaces. Right. Okay, the perpendicular component of the force says acts between the two contact surfaces, and this is a kind of the reaction force. Right, the name itself states that normal reaction, the reaction force, or in another sense, it is also known as the contact force. Right. Okay, a very like simple example I'm going to give in front of you all. Right, two examples. Suppose this is one. Right. Okay, this is an horizontal surface, ground, and object is kept like this way. Right, object is kept like this way. Right, so in this case, right, the perpendicular component of this force, right, I'm not interested whether it is what we can say horizontal exist or not. This perpendicular component, it is known as the contact force, right, or in another, that is known as reaction force. Right, it is something against its weight. Right, so this is a normal reaction. Suppose, let us take an example. If I am having like this way, this is an inclined plane, let us take it is inclined at the 30 degree, right, then object is kept here. Right, suppose this is a mass, right, then this will be the normal reaction. Right, okay, this one N will be the normal reaction. Right, so it's a perpendicular component. See, lots of as usual I used to say lots of definitions and thousands of the resources it is given, right, but this is quite like easy for you all to understand. Right, okay, the perpendicular component of the force between the two contact surfaces, this one is a normal, right, this is a surface number 1, this is surface number 2. Right, against its weight, one reaction we are getting, that is known as normal reaction. Again, its weight or one of the components of the weight, we are getting the normal reaction. Right, as usual, as we say that forces always occur in pair. Right, so like this way situation is. Okay, so we have seen the examples, we have seen the concept of the normal reaction. Okay, and now let's move on to the one sum related to it. Okay, and some sums related to it. Okay, see, a cylinder of weight W is resting on the V-shaped groove. See, this is a V-shaped groove. Calculate the normal reactions between the cylinder and the two inclined walls. Okay, vertical angles are given to be 60 degree, so it means horizontal angles are 30 degree. This two are 30 degree. Cylinder is like placed this way. Right, extremely sorry for my drawing. Okay, cylinders are placed like this way. Right, weight is acting in downward direction. The vertical angle is 60 degree. Right, okay, now suppose if I'm drawing the FBD, if angles from the respective wall, suppose this is a wall A and this is wall B, if angles from the respective walls is same, if angles from the respective walls is same, then what will happen? Right, they are going to exert the same normal from both of the side. As I said, according to the definition of the normal, perpendicular to the contact, angles are same, so they are, see, if this angle, suppose this is 60, this is 30, suppose this side is 60 and this side is 30, then N value is going to be changed, but this is on the same side, so here the value is N. Right, so resolving this component, can I say this is N sine of 30 and this will be N, right, cos of 30. Okay, this will be N sine of 30 and this will be N cos of 30. The horizontal component are going to cancel the effect of each other. Right, the horizontal component are going to cancel the effect of each other. It means that, right, see, this is 2N sine 30. This will be W. System is in equilibrium. Summation of all forces will be 0. So 2n sine of 30, that will be equivalent to W, and we are getting it as a W. And that is a perfect answer for this specific question. And we are getting it as a W. Right? Okay. So now let's move on to the next question of it. Now in this case, system is not in equilibrium. It is moving. On the left side, 200 Newton of forces are applied. On the left side, 200 Newton of forces are applied. Now in this case, right, you can say, right, a net acceleration along the y direction is 0. We can equate, we can summate all the forces along the y direction, but we are having only single value of the force in this, and system is moving towards the left. So for that case, the net acceleration along the x direction is not equivalent to 0. It means the summation of all x forces along the x direction will be not equivalent to 0. Now what will happen? Right, we are going to draw the FBD of this. Okay, let's see. First of all, let's draw the FBD for 25 kg. According to the concepts of equilibrium of the forces, right, we are able to understand that net acceleration is not equivalent to 0 along x. But what will be the direction of the direction of the net acceleration? Will be direction of net force. What is your direction? We are having only the single value of the force, and it is obvious, we are sure that system is going to be moving to the left direction, right? So what will be the direction of net acceleration? That will be into the left side, right? Now, okay, this force is 200 Newton force is acting, right? Now, suppose if I am plotting here, right, 20 kg. Suppose if I am drawing here 5 kg. So obviously there exists a normal between 20 kg and 25 kg. For this block, it will be N1 like this way, and this will be N1 like this way. For this block, it will be N2 like this way. For this block, it will be N2 like this way. This is what it is given. N1 that is acting between 25 and 20, N2 that is acting between 20 and 5. Right? This block is also having the same acceleration. This block is also having the same acceleration. Now let's summation of all x forces. If it is not equivalent to 0, then we can write it as m net along x, right? Along x. So mass is 25, net acceleration is a. In the direction of the net acceleration, the force exists. It is always of the higher magnitude, and opposite to that, it's of the lower magnitude. So whenever we are writing m into net acceleration, so it's 25 is the mass of an object, right, into net acceleration a towards the left side. The force on the left side is always of the higher magnitude, minus on the right side lower magnitude. Equation number 1. Right, equation number 1. Now let's move on, right, to the next part. For second block, right, arey yaar, I'm sorry for that. For second block, you can say this 20. Net acceleration is in right direction. Can I say mass of the object is 20 into net acceleration? In the direction of the net acceleration, the force is of the higher magnitude, N1. Opposite to that, lower magnitude, N2. Can I consider this as equation number 2? Yes. For the third block, mass into net acceleration, that will be summation of all x forces. What is mass? 5. Net acceleration A. In direction of the net acceleration, higher magnitude, minus no other forces 0. N2 that will be equivalent to 5. Right? Can I consider this as equation number 3? Replacing 3 in 2, right? What we got? Replacing 3 in 2, we get 20 of A, that is equal to N1 minus 5 of A. So N1 that is equal to, right, 25 of A. right? Replacing the n1 value in 1, we get 25 of A, that is 200 minus 25 of A, right? So it's 50 of A, that is equal to 200. The net acceleration of the system is 4 meter per second square. The net acceleration of the system is 4 meter per second square. There is easiest way to calculate it also, that net acceleration, that is equal to net force by mass of system. This is another way to calculate. What is net force? We are having only single value of the force, 200, right? Okay, what will be the mass of the total system moving? 50. So the net acceleration is 4. So this is easiest way to calculate, right? Okay, right, and this is the longest way. Now what will be the value of n1 and n2? Very simple. N1, that is n2, this is equivalent to 5a. 5 into 4, 20 Newton. Right, n1, that is equal to 25 into 4, that is 100 Newton. Right, so these are the values of 120 Newton. Okay, 120. The D will be the perfect answer for this specific question. So the first case we saw, right? Okay, if the system is in equilibrium, then how normal is calculated. The second case we saw, if the system is moving, then how normal is calculated, right? Further into the upcoming lectures, obviously we are going to deal with the, right, the craziest stuff. So this will be the homework from my side. This is a very nice sum. The system is again in equilibrium, right? Okay, but you need to calculate the normal reactions at the walls, right? Okay guys, so this will be homework from my side, and answer to this questions, right? You can comment beneath the video, right? Okay, now, so this was the first type of the force. Now let's move on to the second type of the force, that is tension. Tension. What actually the tension is? What actually, right, the tension is? Now let's move on. Have you seen, some students might have seen this game, Squid Game, tug of war, hey, 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 kind of thing, right? Like, hey, 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 kind of thing. What is a tension, right? What is a tension, right? How we are going to deal with that? How the Squid Game is going to help this stuff, right? How the Squid Game is going to help in this stuff. The most important strategy, right? Okay, the most important strategy was followed by this, what we can say, the hero of the Squid Game, right? You can say the grandpa of the Squid Game, that old guy, right? Okay, now how we can correlate this tension force to the example of tug of war, right? How we can correlate to this tug of war, right? Suppose, let us take an example. There is a rope or a string, right? One, see, in the tug of war, what happens? One is applying the force, right, in this direction. Can I consider this as F1? Second is applying the force in this direction. Can I consider it as an F2? Now both side, right, the force is applied. Obviously, right, in tug of war, one is trying to pull the game towards their end. The second is trying to, right, pull the game towards their end. Pull, that is an important word, right? A pull, right, exerted by rope, strings or chain, right? That pull is defined as tension. Pull exerted by rope, chain or any kind of the strings. Suppose in game of a tug of war, one team is trying to pull the right rope towards their side. So against this force, rope is exerting one pull. Suppose if force is applied to this side, against this force, right, a rope is exerting one pull. That pull See, force is nothing else but a right push or pull, right? So this pulling force, it is a tension, right? This pulling force is a tension, right? Let's have an examples of it. Let us take an example. Suppose a block of mass m is attached to the string or a cable and it is attached to the ceiling. In this case, what will happen, right? What kind of the force it is exerted, right? Okay, suppose let us take an example. Its weight is acting into the downward direction. Can I determine it as mg? Right? Against to that weight, this is a pulling force. Exerted by a rope. Pulling force exerted by a rope. Right, here net acceleration is 0, that's why we are equating the vertical forces, right? Because net acceleration is 0. But interestingly, right, we are right talking about the pulling force. That is an important part. Either it can be rope, either it can be chain, either it can be string, but tension is a pulling force, right, that is exerted by this kind of systems. Basically, we are having two kind of systems. As I said about tension, right, in summarized form, it is a pulling force. Basically, for tension, we are having two kind of classification. One, ropes with masses m, right? Second, massless ropes. That is the difference. Arey yaar. I'm sorry, this was a black screen. Tension, a pulling force, right? Okay. One, obviously it is exerted by ropes, but in one case ropes are having masses m. Second, massless ropes. There is a small difference between the massless ropes and ropes that are having the masses m, right? Suppose, let us take an example to understand this, right? Okay, this is a rope of mass m that is pulled by force F and acceleration is along this direction, right? This is a rope with masses m. Suppose a mass m is attached to the rope or a string and it is connected to the ceiling. In both of the cases, what is the difference? What actual the difference is? Suppose if I'm talking about the 3 points, point A, point B, point C. Similarly here at the 3 points, point A, point B, point C. If the ropes are having masses m, then tension at the each point of the rope is not equal. Tension at each point of rope is different. Suppose if rope is massless, tension at each point is same. It means in this case, can I say TA that is equal to TB that is equal to TC? Yes, we can say that. Why? Because the rope is massless and each and equal, right, equal pulling force is exerted at the each and every point of the string if the rope is massless. But at this case, I can't say TA is not equivalent to TB is not equivalent to TC, right? Okay, here it differs. right? So for that reason, into the Pulley problems, it is always mentioned. For that reason, into the Pulley problems, it is always mentioned, right? What it is mentioned? All pulleys are massless and frictionless. All strings are massless and frictionless. All of these things are massless and frictionless. Why they consider everything is a massless and a frictionless? Because tension at the each point of the rope or string or the chain is equal. Similarly, in this case, tension at the rope or the each point is not equal. Why? It is having mass F. We are going to see both of these cases, right? First, we are going to see this, and after that this. But before that, to deal with these cases, right, you are in need or to understand the three type of densities. If the ropes are having mass m, then it is important to understand how masses are distributed to solve this sums easily. For that, we are having three type of densities. First, linear mass density, that is known as lambda. How mass is distributed over length in one dimensional object, how mass is distributed over length. Suppose with respect to the reference point, the length of the string is L. In between 0 to L, how mass is distributed? Is it uniformly distributed? It is non-uniformly distributed. Whether it depends on the equations or not, lot of the things, right, we are going to discuss. So types of density contains first, right, as linear mass densities. Second one, that is surface mass density. Sigma. How mass is distributed over specific area. This is two-dimensional object that contains length and breadth, right? How mass is distributed into the small area element dA. If this mass is dm and this area is dA, then I can also write it as dm by dA. Into the very small element, area element, right? Okay, how it contains and how mass is distributed over specific area. Third, volume mass density. These things, right, are going to quite helpful into the 7th chapter, right? That is rho, that is equal to mass per unit volume, that is dm by dv, right? So this three type of densities are quite important to understand this first case of the tension. So these are the two most important cases of the tension, and these are the three types of densities, right? I'm moving aside because this is a blank screen. You're not going to get into the notes. Don't get worried. You can just have a snap of it, right? It's 5. I'm giving you right on the countdown of the 5, right? You can just, we will move on, right? So it starts 5, 4, 3, 2, 1. Suppose this is a string having mass m, right? Right now I'm not considering this much part of the string, right? I'm not considering, I'm only, right, considering this part. Suppose this is pulled by force F at distance x, right? What will be the tension of this string T, right, at distance x? I'm considering only this much part of the string, right, because the upper one would be the complicated case that we can see in the sums. Now, as usual, according to our discussion, the rope is having mass m. It means that tension at the each point is not same. Then how tension varies? First, it is a case of a uniform mass distribution. It means lambda, mass per unit length of the system, is constant, right? That is equal to dm by dl. Mass is constant, right? Now let's draw the FBT. Suppose at the, see, total length of the string is L. Suppose we need to calculate the tension at a distance x, right? So I am dividing the rope into the two systems, right? Okay, this one will be M1, this one will be M2, this will be X, this will be L minus X. Now tension is a pulling force. Pulling force, it means direction of the tension will be like this way. Pulling force, it means direction of the tension will be like this way. Force is acting in this direction. What will be the direction of the net acceleration? Direction of the net acceleration will be in this direction according to the conditions of equilibrium of the forces. Right? We are having the acceleration into the x direction. It means summation of all forces along the zero, that will be m into a net. If I'm using this first equation, mass 1 into net acceleration, m1 into a, right? Can I write it as force in the direction of the net acceleration, higher magnitude, minus lower magnitude. Similarly, for this second, forces in the direction of the higher magnitude, right? Opposite direction, we are not having any kind of the forces. Can I consider this as equation number 1, right? And can I consider this as equation number 2? Yes. Now, as we said, uniform mass distribution, lambda is constant. It means what? Lambda is constant is equal to mass per unit length is equal to what? M1 by X, M2 by L minus X. I can write it down, na? Right? If lambda is constant, right? And if mass per unit length is constant, mass is uniformly distributed over length. So can I write it as M1 that is equal to Mx by L, M2 that is equivalent to what? Right, M2 that is equivalent to M into L minus X by L. Right. So here, and obviously the net acceleration, it is going to be F by M, because it is net force by mass of the system. Mass of, see, net acceleration, we are having net force F by mass of the system is M, right? Okay, now we need to calculate the tension. Tension T is equal to M2A, right? Can I replace the value of M2? M2 value is M by L into L minus X, right? A. Can I replace the value of the net acceleration? Because this is unknown, we need the answer in terms of F. A is unknown. A is an intermediate physical quantity. We need an answer in terms of F. So can I write it as M by L into L minus X, right, into F by M. This mm is gonna, right, this is the tension, right? This is the value of the tension. Right, this is how it is calculated, right, using the equilibrium of the forces, right? Okay, the cases of tensions having mass m, right? Okay, now, so guys, this one and this one, this two, right, okay, you can do, it's not a big deal, because we need to cover the lots of part. The most important from this, right, okay, the most important part apart from this is like this one, right? This we can do, okay, this we can do, it's not a big deal. Okay, now let's move on to the Pulley problems. Let's move on to the Pulley problems, right? In a maximum number of the cases of the Pulley problems, right, one word is used. All ropes are massless and frictionless. All pulleys are massless and frictionless. Pulley, it is also known as, sometimes it is also known as Atwood machine. And lots of technical words are there, but we are not interested in that, right? We are only interested, right, into the, right, what actually the concept says, right, what actually the concept says. So pulley problems. All ropes are massless and frictionless. All pulleys are massless and friction. So in this, all of these cases, we are directly going to deal with all of those stuff, right? In which all of the cases, right, the pulleys and ropes are massless and frictionless, right? Okay. So these two most important statements, right? Again, I'm writing here all ropes, right? All pulleys, massless and frictionless. We are going to solve this sum by means of right. We are going to understand this sum by means of this the sums only, right? We are going to understand this concept by means of the sums only, right? Okay, see, two bodies of mass 4 kg and 6 kg are connected to the ends of the massless string. See, it is given massless. In maximum number of the cases, it is massless. The string passes a overlay which is frictionless. Oh, that is frictionless. See the figure. The acceleration of the system in terms of gravity will be what? NEET 2020 they have asked. Very simple sum it is, right? Very simple sum. 4 kg, 6 kg. First of all, I want to ask you all, in which direction the particle is moving? Obviously, this is of the high weight. It means it is moving in this direction, and this is of the less weight. Then the system, this 4 kg is moving into the upward direction. Right, this is just a common sense, right? That 6 kg, right, it is of the higher mass, so it is moving into the downward direction, and 4 kg is of the lower mass, then it is moving into the upward direction. Now what will happen here? First of all, let's draw the FBD. This is 4 kg, right? This is 6 kg. First point, their weights are always acting into the downward direction, right? 4g, 6g. Tension is the pulling force. They both are connected by the same string. String is massless. It means tension at the each point on the string will be same. Tension at the each point on the string will be same, right? Because string is massless, as I told you before, right? It is a pulling force. It is a pulling force. So for 4 kg, it will be pulled in upward direction. For 6 kg, it is also pulled into the upward direction. Tension is a pulling force. Now, if 4 kg is moving into the upward direction, it means the net acceleration will be like this way, and net acceleration in this case will be like this way, right? Net acceleration in this case will be like this way. Now, summation of all horizontal forces till now we have seen summation of all horizontal forces are 0, summation of all vertical forces are 0. After that, we saw one example into the normal reaction, that summation of all horizontal forces are not 0 but vertical are balanced. Here there is no horizontal force, only vertical forces are there, so it means net acceleration along the y direction is not equivalent to 0. So the summation of all forces along the y direction will be equivalent to ma net, right? Ma net. Okay, first of all, we are taking 4 kg. So ma net, that is equal to summation of all y forces. What is mass? 4 kg. What is net acceleration? A. In the direction of the net acceleration, force is of higher magnitude. Opposite to that, lower. Higher, lower. Can I consider this as equation number, right, 1? For 4 kg block, right? Suppose if I am moving on to the 6 kg block. Suppose if I am moving on to the 6 kg block, right? So can I write it as mass into net acceleration, that is equal to summation of all Fy forces. Mass is 6 kg. Net acceleration is what? Right? A. Force in the direction of the net acceleration is of the higher magnitude. Here 6g is the higher magnitude minus lower. Equation number 2. Can I equate them, right, to calculate the tension and the net acceleration, right? So it's 4a is equal to t minus 4g. 6a that is equal to 6g minus t. Right, so it's 10a, that is equal to 6g minus 4g, right, that is 2g. A is equal to g by 5. The net acceleration of the system is g by 5. Right, the net acceleration of the system is g by 5. If you don't want to equate it, right, you can we are having the second procedure also. If you don't want to equate it, right, okay, so you can just replace it also. Suppose t is equal to 4a plus 4g, 6a is equal to 6g minus, can I replace value of t as 4a plus 4 of g? So it's 10a is equal to 2g, again a will be g by 5. This is the second. You can replace second equation in one or one equation in second, right? Okay. Now what will be the value of the tension if a is equal to g by 5? It's very simple, right? We are going to get the tension as, right, 4a plus 4g, right? So it's 4 of a plus g, right? So tension will be 4 into is g by 5, right? So 6g by 5, right? So 60 by 5, 12, 48 Newton will be the tension, right? Acceleration is g by 5, tension will be the 48 Newton. Okay. Second sum. Let's move on to this kind of the concept, right? And calculate the tension. The equal weights, right? See, first of all, we are going to move on with the fixed pulleys. See how tension rules, mass, massless. Right, masses, we did the calculation, we moved on to the types of densities. Massless, right, fixed case, movable pulleys, like this way. See, I'm going to show you the tension, right? Masses, massless, massless, fixed pulleys. For movable pulleys, we are having constraints. Like this way the flow chart follows, right? Like this way the flow chart follows, right? Now let's see this question. The three equal weights of 2 kg are hanging on the string passing over the fixed pulley shown into the figure. What is the tension into this? Okay, between B and C, right? What will be the tension? String changes, tension changes. See, all the strings are massless. A and B, they are connected by the same string. So the tension at the each point will be same. At this side, tension at the each point will be same. But B and C, they are connected by the different string. I can understand it is a massless, right? But still tension will differ because tension is the pulling force. So between B and C, we are having the tension as T1, right? So let's discuss each of the masses are 2 kg. See here, it's B, it's A. 2 kg, it means their weights is acting in downward direction. 2g. The weight is acting into the downward direction. Obviously, they are connected by the same strings, right? So they are having the same pulley force, T, right? Okay, now here we are having C. C is also, right, 2 kg, so its weight is acting into the downward direction, that is 2g, right? Now see, between B and C there is a string, right? So in between them, right, there is also one pulling force, right, that is pulling C towards upward and B towards downwards, T1. Now most important, what is the direction of the net acceleration? Obviously, on the right side of the system, we are having the higher masses, right? So A will move into the upward direction with net acceleration A. B will be moving with the downward direction, and this will move with the downward direction with acceleration A. Right? Directly write down for the equation. For A, can I write what is the mass 2 kg into net acceleration A? In the direction of the net acceleration, force is of higher magnitude minus lower 2g. For B, right, can I write mass 2, acceleration A, right? In the direction of the net acceleration, we are having, right, forces of higher magnitude T1 plus 2g minus lower magnitude T. Similarly, this mass 2 kg in the direction of the force we are having 2g, right, minus T1, right? So can I write it here as T1 that is equal to 2g minus 2a. Can I consider this? See, can I consider this as equation number 1, right? Can I consider this as equation number 2 and this is equation number 3, replacing 3 and 2. Can I say 2a that is equivalent to what? Right, 2a that is equal to T1 plus 2g, right, minus T. Can I replace 2g minus 2a? So it is 2g minus 2a plus 2g minus T. So 2a that is equal to 4g minus 2a plus, sorry, minus T, right? So T will be equivalent to 4g minus 4a. Can I replace this in equation number 1? Yes. 2a that is equal to T minus 2g. So 2a that is equal to 4g minus 4a minus 2g. So it's 2g 6a. A is equal to g by 3. Net acceleration we got it as g by 3, right? Net acceleration we got it as g by 3, right? Now we are going to replace and get the values of, right? What will be the tension? See, we need to calculate a tension between, it's 2g minus 2a, right? It's 2g minus 2a. So can I write T1 that we need to calculate 2g minus a. So it is 2, right, g minus, right, g by 3. So it's 2 into 2g by 3. It's 4g by 3, right? This will be the tension into the string B and C, right? 4g by 3. If you want to evaluate it, right, it's 40 by 3, right? Yes, approximately it is 13.3 Newton, approximately. 13 3 is a 39, na? Right, 40 by 3, so it's approximately equivalent to 4g by 3. If I'm taking exactly g value, right, then we are getting 13.3 Newton as a perfect answer, right? So this is how this sum is evaluated. Now let's move on to the next sum, right? These are all the basic Pulley problems you all are aware of. After that we are going to see the constraint methods, right? After that we are going to see the 3 methods into the constraint, and slowly we are going to solve these sums, right? Okay, I think okay, let's move on, right? As you can see, right, approximately, right, 2.5 hours of the lecture has been completed. Okay, now let's move on to two bodies of masses 5 kg and 4 kg. They are arranged, right, and the tables are perfectly smooth. Ropes are massless and frictionless. The bodies into the case, the accelerations into A and B will be what? Right, see, it's a very simple thing. Same procedure we need to follow. Here, obviously the 4 kg is like this way. The system will move like this way because all the surfaces are frictionless. And here the system will move like this way. This will be the net acceleration, right? And this will be the right net acceleration into the upward direction. And for this kg, net acceleration will be in downward direction. Tension is the pulling force. Tension is the pulling force. Tension is the pulling force, right? Tension is the pulling force. Can I consider this as case A and this as case B? Let's write down the equation for case A, right? For A, can I write down the two equations? Simple, right? 4g that is acting into the downward direction, mass into net acceleration, 4a, right? Okay, mass into net acceleration. In the direction of net acceleration, we are having the force of the higher magnitude. 4g net acceleration is downward direction, the 4g is in downward direction, so it is of the higher magnitude. For this, phi a that is equal to T. 9a is equal to 4 of g. Acceleration in the A that is equal to 4g by 9. right, we are having, I think we got the option, but it's okay. We are going to identify for B also. So in this case, acceleration is 4g by 9. Now we are going to write down this for this equation, right, for 5g, and this is for 4g. This side net acceleration is in downward direction, so phi of a, that is equal to phi g minus t. For this, the net acceleration is in upward direction, so it is 4a is equal to t minus 4 of g. This t is gonna cancel. This is g, 9a, a in the case of b, that is equal to g by 9. Acceleration into the A case is 4g by 9, B is a perfect answer. The simple Pulley case problems. Right? Kerala PMT 2002, one sum came on Lami's theorem. Exciting theorem is that, right? It's quite... A body of weight 2 kg is suspended as shown into the figure. The tension T1 into the horizontal string will be what? Tension T1 into the horizontal string will be what? Right? Okay. Tension into the horizontal string will be what? Let's first of all, let's understand this Lami's theorem. What does the Lami's theorem states? Lami's theorem states that first, system should be in equilibrium. Second, only 3 forces should be there. F1, F2, F3, alpha, beta, gamma. The resultant of the 3 forces is always 0 because system is in equilibrium, or in another sense you can write it down F1, right, by sine or alpha. If you are considering this force F1, then angle should be, right, angle should be in between the rest of the 2 forces. If we are considering F1, right, then angle should be between F2 and F3. If I am considering F2, then angle should be right between F1 and F3, that is sine of gamma. If I am considering F3, then angle should be between F1 and F2, that is sine of beta. This is what the equation of the Lami's theorem is. How to identify whether right to apply the Lami's theorem or not? How to identify whether to apply the Lami's theorem or not? There is an existence of the 3 forces at a junction, right? And the system is in equilibrium, the net acceleration is 0. This is what Lami's theorem is all about, right? So in some of the cases we can directly use, right? In some of the Pulley problem also we can use this theorem, right? Okay, so now let's move on to this, how to solve this stuff. First of all, let's draw the dB. See, suppose here if the tension is T, right, then obviously this is 2G. So this value of system is in equilibrium, this T will be equivalent to 2G. I'm talking about one junction. T1 is in this direction, 2G is in this direction, T2 is in this direction. Suppose this is 30 degree, this is 60 degree, this is 90 degree, this is 90 degree, this is 90 degree. System is in equilibrium also, and at junction 3 forces are there, 2G, T1 and T2. System is in equilibrium also, and the junction, right, 3 forces are there. Right, directly we are going to apply the Lami's theorem. Suppose if I am writing T2, right, the forces between them, sine of 90. If I am talking about T2, then forces between T1 and 2G, sine of 90. Right, if I am talking about T1, forces, the angle between the rest of 2, that is sine of 90 plus 30. Right, and if I am writing, right, 2G, Okay, then angle between them sine of 90 plus 60. Right, so this is what the Lami's theorem is all about, right? Again, I'm going to write the equation T2 by sine of 90, that is T1 by sine of 90 plus 30. So T1 by sine of 90 plus 30, that is cos of 30, right? And 2g by sine of 90 plus 60, that is T2 whole, 2g, right, whole divided by, right, cos of 60. Now, consider this is equation 1, this is 2, right, this is 3. Compare 2 and 3, because we need to calculate the tension in horizontal stream. T1 by cos 30. Cos 30 is root 3 by 2. And that is equal to 2g by, right, half. This half is going to cancel. T1, that is equal to 2 root 3 of g. Right? 2 root 3. Okay, it's kg weight. Right? It is asked in kg weight. So it means C will be the perfect answer. This is, we are getting in Newton. Right? To convert into the kg weight, you can just replace G. You can just remove G. Okay, so it will be converted into the kg weight because we have asked into the kg weight. Right? So 2 root 3 C will be the perfect answer. Kerala PMT 2002 question. Right? Okay. Now, let's move on to the next question of this. This is asked into the AIEEE 2002. So this is my homework question. Right? You can easily solve. Right? Okay, you can answer this question within the video. Now, what if the constraint relations are there? What if? Right, I'm talking about the constraint relations. Constraint relations mean what? Right. What cases are included in this? So if I'm talking about the constraint relation, first of all, constraint relation is means what? One is restricted to move as because of another. One is restricted to move as because of another. Constraint, the word itself states that. Constraint. Second, maximum number of the cases this happens in the case of movable pulleys. See, you can see in this visualization, someone is trying to pull. So as because of this object is constrained to move into the upward direction, is forceful to move into the upward direction. Right? So this is the case of the constraint relation. Right? This is the case of the constraint relation. Basically, there are some methods into the constraint relation and there are some sign conventions. We are directly going to deal with all of those stuff. Right? Okay, see, 3 methods are there. First of all, the most important method is length of string. This is the most important method. But this is so lengthy, right? Then it is going to consume your maximum amount of the time of the paper. It is that much lengthy. Right? So I never used to discuss this, right? We are directly using this 3 important, right? Okay, the first one is a method of work done by tension. Second, it is a method of general constraint, right? And third, up to the advanced level, we are having the wedge constraint. The 3 important techniques are there. The 3 important techniques are there. Work done by the tension, general constraint, wedge constraint. Apart from, see, the length of the string method. Using the length of the string method, we can even calculate, we can solve all of those sums, right, of the general constraint and work done by tension, right? We can solve all of those sums, right, of this, okay, and this by using the length of the string method. But this is quite complicated, right? This method is quite complicated and it is really really at the first sight, it is really, right, no one is unable to understand that. Wedge constraint, it is a simple. So for that reason, right, we are discussing directly 3 shortcuts one by one. Right, work done by tension. First of all, let's have this example, right? Let's have this. Suppose this is a pulley. This kind of the system it is given, right? If I am talking about our previous cases, right, a simple classification, simple differentiation I'm going to give you all. See, in all of these cases we saw, right, okay, in all of these cases we saw, see, in both of the objects, right, accelerations, the net accelerations values were same. You can see here we have taken A, here we have taken A, right, here we have taken this in both of these cases, right, here we have taken upward A, downward A, like this way A, right? Why? Because both blocks were connected to the same string that were crossing over a single pulley that was fixed. It wasn't a case of movable pulley, right? See, in this case, pulley is movable, right? This pulley is movable. So it means that, see, this is fixed. This is going to be into the accelerate towards the right direction. This is going to accelerate it in the downward direction, but these accelerations will be different. This will be A1, or you can consider, right, this as A2, and this is A1. Right, acceleration of the both will be different because they are not connected even to the same string. Even they are connected to the same string also, then also, right, as there are some cases, we will discuss this, don't get worried, right, as they are connected to the movable pulley, right, the things get differ. How work done by tension, we are going to use that. For 2m, suppose if I am drawing the FBD, right, see, tension, it is in upward direction, right? Okay, now suppose this 2MA is taking the displacement dA1, or you can say suppose it is having the displacement, right, dx1 into the downward direction, slightly displaced by dx1. Similarly, if I'm talking about mass m, the tension is acting like this direction, and suppose it is, right, displaced dx2 in this direction. 2m is displacing in downward direction and this is displacing in right direction. So are tensions in both in equal? No. Suppose here if tension is acting as T, so it means here tension is T, this will be T. To balance the situation, right, here tension will be 2T. So here the actual tension is 2. So first step is to draw the FBDs, right? First step is to draw the FBDs. Here draw. Now, work done by all tension is 0, right? Work done by all tension is 0. Let's see it here. Work done by all tension is 0. For this block, what will be the tension? 2T. What will be the acceleration? A1. So can I say, let's move on to the, for it's 2T. See here. The force 2T is acting in upward direction, displacement is in downward direction. Force and displacement, they are both in opposite direction. Work done will be negative. So this will be negative of displacement dx1. Here T is in right direction, The displacement is in right direction. So work done is positive. T into dx2 is 0. Can I equate 2t, that is dx1 is equal to t dx2. Tt is going to cancel. 2 dx1 that is equal to dx2. Can I differentiate with respect to time? I will get 2 of v1 that is equal to v2. Again differentiating this stuff, right? I'm getting the acceleration 2 of a1. That is the constraint relation. How one is restricted to move as because of another. By what equation I can represent that equation, right, is known as constraint relation, like this. Work done by tension is always 0. Right? Work done by tension is always 0 in this system. I'm talking about the entire system, not about the individual particle, right? I'm talking about the entire system. Right? Don't get worried, this was an initial stage, right? Okay, so we are having the two important things, right? We are having the two important things. First, either we can directly use, say this is a work done by tension sigma t dot dA, the product of tension and displacement. If really you want to pile up this thing, simple. Tension acceleration of 1, tension acceleration of 2, that's it. For the two blocks, what will be the tension of the two blocks with the respective acceleration? Just compare directly to get the constraint relation. See how easily we are going to use this method, right? Okay, to solve this stuff. Very simple. Suppose tension is T, right? The same string tension will be T, here tension will be T, here tension will be 2T. Obviously, okay, see the blocks A and B having masses respectively are connected by the arrangement shown into the figure. Calculate the downward acceleration of the block B. Assume that Pulley's, see they have asked downward acceleration of the block B. So this is, let us take an example. This is acceleration of AB. This is acceleration of A1. Simply we are going to write, okay, simply we are going to discuss. See, summation of T dot dA, right, that is 0. Directly we are going to compare T1 A1 that is equal to T2 A2. Tension on this will be 2T. Right, A of 1 that is T or A of A and that is T A of B. So we are having the constraint relation of twice the acceleration of A that is equal to twice the acceleration of B. Now why this is happening? Because mass of B is greater than mass of A. Generally A has to move downward. But there is a possibility that mass of B is greater than A. That's why it is pulling entire system in this direction. Under what condition will under what condition the A will move into the downward direction? If mass of A will be slightly greater than B. Slightly or slightly greater or less than B. Right, under this condition it will move into the downward direction. Right, see now, same thing we are going to use for this kind of the complicated equations. Very simple, direct constraint relation. This is a A2 and this is A1. See, in this A1 is moving into the downward direction. Suppose this is tension T, this will be the T. Right, this will be T, 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 because all strings are same, so and they are massless, so the tension at each point of the string will be equal. So if this T, this will be 2T, this T, this will be 2T, this T, this will be 2T. So we are having the system like, right, this is an object having, right, acceleration A1, tension is 60. This is A2, tension is T. Directly work done by tension. See, work done by tension states, right, the product of tension and displacement is 0, the net. We can differentiate it twice to reach from displacement to acceleration. But to save our time, we can directly use that stuff. What? T1 A1 that is equal to T2 A2, right? 6, right, of T of A1 that is equal to T of A2. T is going to cancel, right? We are going to have the constraint relation as 6 of A1 that is equal to A2. This is how constraint relations are obtained, right? This is how constraint relations are obtained, like this way. This we have seen, right? Now in this we need to calculate the acceleration. Till now we have seen, right? Till now we have seen how to obtain the constraint relation. See, first of all, let's obtain it. Suppose this is T acting in this direction. This is acceleration A2. Suppose this is T at 2T. This is T, then this is T, this is T. T to balance this we are having 2T. And this will be A1 into the downward direction. So according to the constraint relation, sigma T dot dA is equal to 0. T1 A1 that is equal to T2 A2. Right. So can we have, right, T of A2 that is equal to 2T of A1. T is going to cancel. We are having A2 that is equal to twice of A1. Right. What we need to calculate? We need to calculate the A2. We will. Let's draw the FBD. This is A2. For this, I am going to write the summation of all x forces is equivalent to m into net acceleration T. Equation number 1. Right. For this block, 2m. A1 that is in downward direction, 2T that is in upward direction, 2mg that is in downward direction. Right. So for this I can write 2m A1 that is 2mg minus 2T. So we are having the two equation. First one that is T is equal to m of A2. Second one m A1 is equal to mg minus T. M A1 that is equal to mg minus T. Right, let's evaluate it. Right, it's T m A2. Right, T is gonna cancel. Right, m is gonna m is gonna cancel. So G will be A1 plus A2. What we need to calculate? We need to calculate A2. Can I replace A2 as 2A1? Right. See, suppose A2 as 2A1. This is what constraint relation is, na? So we are going to replace this relation here. So A1 will be A2 by 2. So G will be A2 by 2 plus A2. So it's 3A2 by 2 is G. So A2 will be 2G by 3. B. Into the fixed pulleys, acceleration of both were same. Into the case of movable pulleys, into the constraint relation, acceleration of both are different. So in case of the simple pulleys, what we are doing, right? Okay, see, I'm going to show you all, right? In case of the simple pulleys, see, in the case of simple pulleys, what we were doing, right? We were doing, see, this is acceleration of first, second, both are equal, right? We were just comparing the equation, right, and getting up the answer. Just one extra step we need to do into the case of the constraint relations, right? What kind of an extra step, right? Let's see. See, accelerations are different, so the extra step is to obtain the constraint relation. Same, we have to apply the equilibrium of forces for both, summation of the x and y forces kind of thing, right? We obtain this two equation and one extra step to add the constraint to replace the constraint relation in this to get the acceleration, because acceleration of the both will be different. Find the relation between the acceleration of the blocks into the figure. The pulley and the strings are massless and frictionless. Okay, method of general constraints, what it states. See, before that we moved on, right, to the some of the important, the first method that is work done by the tension, right? General constraints, right? It is having two kind of shortcuts, right? First of all, that is a pulley based shortcuts, right? The first one, that is a pulley based shortcut,
right? Okay, now let's see what it states. See, I'm directly write it down, Pulley shortcuts. See, this kind of the things, right, can be easily solved by means of the length of the string method also, right? This kind of the things can easily be resolved by method of the strings also, but right, that as I said, that procedure is quite long. So this is very simple. Suppose this is a pulley. I'm talking about the complete movable pulley, right? This arm, right, it is having the velocity v1. This arm is having velocity v2, and this arm, let us take an example. Okay, let's erase it. Let's keep it this v, right? Okay, this is v1 and this is v2. Similarly, if we are talking about the acceleration, then this arm is having acceleration a1, this arm is having acceleration a1 and a2, right? I'm going to show you the shortcut first, and we are going to discuss the sum, right? Okay, so yeah, we are having the two equations. What kind of this what are those? V is equal to v1 plus v2 whole divided by 2. This is the first constraint relation. Second, a is equal to a1 plus a2 whole divided by 2, right? This is the second constraint relation, and it can be obtained, right, by means of this movable pulley method. Sorry, the movable pulley length of the string method. But generally we are not interested into the theoretical approach, right? So that's why we are right directly right using this shortcut. We are directly using this shortcut, right? Now in this method, right, the most important stuff is of the sign convention, right? Okay, the most important stuff is sign convention, right? How to apply it, how to get through the sums, right? I'm going to right show you all. For sign conventions, we are having the very simple stuff. If the vector is in upward direction, we are having positive. If the vector is in downward direction, we are having it as a negative. If vector is in the right direction, we are saying it as a positive I. If vector is in left direction, we are saying it as a negative I, right? Sign conventions, equations, and we are going to solve the sums. Now let's move it. Let's have an example of it. Suppose this is a thing is given. Right? Suppose this thing is given. It is given that velocity of this arm is 5 meter per second. Velocity of this arm is 1 meter per second. What will be the velocity of this arm? This is a kind of the constraint relation. A simple example, right? Not as much as difficult what we are thinking right now. Okay, so first of all, we are having the two pulleys, pulley number 1 and pulley number 2, right? So we need to apply the shortcut first of all for pulley number 2, right? For pulley 2, right? See, this arm is moving downward with 5 meter per second, right? This arm is moving upward with 1 meter per second, and in another sense, this arm will move downward. Whether it will move downward or upward, right, according to my experience I'm saying, but we'll apply the formula and get it. According to our shortcut, v is equal to v1 plus v2 whole divided by 2. v1 is in downward direction negative, v1 is in upward direction positive whole by 2, v is in downward direction, that is equivalent to 2 meter per second. So here the velocity of this arm is 2 meter per second. Negative indicates, according to the sign convention, it is moving into the downward direction. If now see, this strings and this strings are same. If this is moving into the downward direction, then tension at the each point will be same, right? With respect to that, the string is completely massless. Obviously, all the motion parameters on this will be same. So this will right, okay, this is moving downward, so this will move upward with the 2 meter per second speed. A very simple explanation and the use of the formula. The first sum. Sometimes students are so right, see, after practicing, right, they used to get a habit for solving this kind of stuff, right? They used to get habit to solve this kind of stuff very easily, right? Suppose I'm taking another example for this. right? Okay, this is also movable, right? This is also movable. Let us take an example. This is also movable. What will be the velocity at this end? Suppose this is 6 meter per second, right? This is 1 meter per second, right? Okay, let us take an example. I'm releasing it, right? Okay, this is okay, 2 meter per second upwards, right? This is 1 meter per second, right? And this is 8 meter per second upwards, right? This is the situation given. Now 3 pulleys are there, 1, 2 and 3. For 3 pulley, can I write directly the equation V is equal to V1 plus V2 whole divided by 2. 6 into the downward direction, 2 into upward, minus 6 plus 2 whole divided by 2. So this will, we are having into the downward direction as 2 meter per second. Similarly for this, right, 8 minus 1 whole divided by 2, right? So this is 7 by 2, right, into the upward direction. Now we are having the pulley as like, this is a movable pulley, this is V, right? This is 7 by 2 into the upward direction, right? And this one, that is 2 meter per second into the downward direction. So V will be equivalent to negative of 2 plus 7 by 2 whole divided by 2, right? Negative of 2 whole divided, right? So this will be V is equal to, right, 3 by 4 meter per second. So what will be the velocity at the top? 3 by 4 meter per second. Positive, it means it is moving upward, right? So this kind of the first shortcut of the general constraint is. Second shortcut, suppose this kind of sum has been asked. Right? This is theta 1. This is theta 2, this is velocity V1 and this is velocity V2. See, one is restricted to move as because of another. This is the second method of the general constraint in which we are going to see. See, they are connected by the same strings. How we are going to solve this type of sums? Note. How we are going to solve this type of sums? The component of velocity that lies along string is same. Why? Why? This is a note to solve this sum. This is a kind of a shortcut to solve this sum. It's not a big deal, but why? Why the velocity components that lies along the right string are same? Because string is massless. Tension on each point is same. This we are completely aware of. String is taut. It is not loose. It is completely taut. And when the string is completely taut, both are restricted to move in the respective directions. Then the velocity components that lies along the string do not contribute into the motion of this two. And for string to be completely taut, that components are equal. So it means that if I'm drawing FBD for this, right, if I am drawing FBD for this, see, suppose this is right block 2, right, if I'm extending this is theta 2, right, okay, so it is moving like this way. This is V2, okay, so this is also theta 2. So this component will be V2 cos of theta 2. Similarly, this is V1, right, and this will be V1 cos of theta 1. So the components of the velocity that lies along the string, right, you can see this lies along the string, this lies along the string, they are equal, right, because string is taut and it is massless, right? So what will be the constraint relation? V1 by V2, that is equal to cos theta 2 by cos of theta 1, right? So this is the second method of the general constraint. The first method I show you all for the Pulley, that shortcuts, right? The second method is this. Now we are going to solve this sum, right, according to this method. See, in a figure, a ball of mass m1 and a block of mass m2 are joined together with an inextensible string. Ball can slide over this if v1 and v2 are the respective velocities of the given, then determine the constraint relation between two. Determine the constraint relation between two. Strings are taut. Simple, you can just memorize it as the strings are taut, so the components that lies on the string are equal. Strings are taut, so the components that lies along the strings are equal. Simple. How to solve this sum, right? Okay, note components, velocity components, or you can say the parameters, or you can say simple, either it can be anything, right? We are just simply defining it as a components that lies on string are same. So it means that suppose if v1 is in this direction, I'm extending this line, so this one will be the theta, right? So d1 will be v1 cos of theta, this is v2, right? So both of the components that lies on the string, na, simply I can write it as v1 cos of theta, that is equal to v2, right? This will be my perfect answer, right? So this is the second method of constraint, right? So first we moved on, right, to the very simple, right? The work done by tension is 0, right? Work done by tension is 0, and after that we moved on to the method, two most important shortcuts of the general constraint, right? And now we are moving forward to the right wedge constraint. Like general constraint is having one concept, like sigma t dot dA is having one, right, main concept. The wedge constraining is also having the Brahmastra. As I said before, that's two strings. See, into the previous question, suppose, see, let us take a very simple example. In this, one is restricted to move as because of another. One is restricted to move as because of another. So in this case, what is happening? The components that lies on the string, as the string is completely taut, both blocks are connected to it, so the components are equal. This thing we need to keep up into the mind. The same thing is happening into the next part, into the concepts of the wedge constraint. See, let us take a very simple example to understand this. Suppose this wedge is given the force towards the right side. If this is given the force towards the right side, then and then this block has to move up. Suppose if this force is given to the right side, then block has to move up. So as because of this block, the upper one is constrained to move. As because of the horizontal, the vertical is constrained to move, right? It is constrained to move, right? Okay, now let's, one is restricted to move as because of another. The horizontal is applied the force, and as because of that, vertical is restricted to move. But you can just have one thing. Vertical is like adjusted this way, right? And horizontal is like adjusted this way, right? This is how you can see, right? The one thing is common in both. They are not leaving contact with each other. Right? They are not leaving that contact with each other. Right? So as because of this is an important concept. Right? Suppose, let's take an example. Right? This is a vertical and he has to move into the upward direction with acceleration A. Right? This is an horizontal, right? And it has to move right side with the acceleration A2. Right? So whatever the components that lies, right, perpendicular to the contact surface, right, the components of the acceleration that lies, right, the components of the acceleration that lies perpendicular, here I'm writing the statement relative of, right, I'm writing down the statement again, I think it's visible or not, okay, relative of components that lie perpendicular to contact surface is 0. Why? Because both of the blocks are restricted to move, but still they are connected by any intermediate thing. In previous case, right, they were restricted to move with respect to each other, but they were connected by strings. In this case, they are restricted to move with respect to each other, but they are connected by the contact surfaces. So perpendicular component will not contribute into the motion with respect to contact surface. Right? So it means that suppose this is theta, right? So this is A2, this is also theta, this component will be A2 sine of theta. Right? Similarly, the upward is A1, right? So with respect to this, okay, this will be A1 cos of theta and this will be A1 sine of theta, right? So similarly, right, I will write this into the right appropriate manner. See, perpendicular, right? This is A2. If this is theta, right, okay, then this one is theta. So it means that this will be A2 sine of theta, right, and this will be A2 cos of theta, right. Similarly, the upward is A1, right. So this will be, right, A1 cos of theta and this will be A1 sine of theta, right, okay. Okay, hope so. If I am not done anything wrong, the upward is A1, right? Let's see. Okay, see, this upward is A1 and this is theta, right? And this is theta. Yes, this is theta, right? Okay, it's exactly perfect, right? So it means that it's very simple, right? It's very simple, right? Okay. The perpendicular component of this, it is A2 sine of theta. Perpendicular component of A1, that is A1 cos theta. Relative of this is 0. A1 cos of theta, that is equal to A2 sine of theta, right? So A1, that will be equivalent to A2 tan of theta. This is the wedge constraint problem. Wedge constraint. Okay. Don't get worried. We are going to see the two examples related to it. Right? Find the relation between it's not plus, it's A and B, right? The same thing we need to keep into the mind, as both of the objects are not leaving their contact. So relative of perpendicular components along the perpendicular components across the contact is 0. Let's draw the FBD for this. This is a contact. One that is in downward direction, that is A. Second that is into the right direction, it is B. Right? Okay. Now suppose this is theta. Right? If this is theta, I am plotting up the components. Right? This will be B of cos of theta. This will be B of sine theta. Right? Okay. This will be, right, B sine theta and this will be, right, okay, it's simple. This is a contact, this will be our contact surface, right, this will be our contact surface, right. Now suppose this is A, then this will be A of cos of theta and this will be A of sine of theta. Relative of perpendicular components, relative of A cos of theta minus B sine of theta is 0, right? Relative of perpendicular components, relative of perpendicular components, right? Relative of perpendicular components, right? So it is a cos theta, that is equal to b sine of theta, right? So a is equal to b tan of theta, right? And that is the perfect answer for this question, right? That is the perfect answer for this specific question, right? A is equal to b of tan theta, right? A cos theta, b sine theta. Okay, you can just see, right? We're drawn this component, right? Okay, now let's move on to the another example. See, same thing. This A is moving onto the downside, B is moving towards the right side, right? So this is a homework, right? You can solve it and answer beneath the video, right? So this is a complete the tension part is. This is the complete tension part is, right? Okay. After that, I think yes, we are moving forward to the frictional force, right? Okay, now first of all, let's see what we have done, right? So here it is the end, right, of the complete tension part. Again, lots of the wedge constraint problems are also there, but I think we are limited, we are having the limited time, right? And so we are doing this year up to here only. Okay, so now let's move on, right, to the different concept, right? Okay, of the frictional, right, force, frictional force. So till now we have seen the important concepts, right, of this chapter. We have seen many type of the forces, right, like a normal reaction and tensions and everything. Okay, now let's move on to the most important part, that is a frictional force, friction. First of all, I want to write down some of the noteworthy points related to the frictional force, right? The first most important point is it always, right, opposes the relative motion between two contact surfaces. Second point, it is an electromagnetic force. Why it is known as the electromagnetic force, right? We are going to show, right? In another sense, it is interlocking between two surfaces. Right, some of the noteworthy points related to the friction. Okay, now let's understand all of these points, right, with the help of an example, right? Okay, you can see the visualization. Mobile is sliding down and after some amount of the time it stops sliding. Why? Between two contact surfaces we are having, right, something that forces us to stop, right, that opposes the motion, the relative motion. How? Suppose let us take a very simple example. This is a ground and this is an object M. I'm talking about the contact. There exists a, right, there exists interlocking. This is an interlocking between two contact surfaces, right? Interlocking between two contact surfaces like this way. This is the first, this is mass M, the bottom surface of mass M, and this is a horizontal surface. So that is all, there exists always an interlocking between the two contact surfaces, right? Okay, that don't allow the relative motion between them. That is a frictional. Right. Frictional force is not kind of an opposing force, or right, the students are having this kind of the conception, right? Object is moving like this way, the force that is opposing the motion is friction. No, force that opposes the relative motion, force that opposes the relative motion, that is a frictional force. So first, it is an interlocking. This interlocking is as because of presence of charges. First, we saw there exists interlocking between the two contact surfaces. This interlocking is just because of the charges present nearer to the charges in contact. They exert, right, towards each other, right, one electromagnetic force that charges, right, exerts, right, the charges that are present on the two surfaces. They exert the electromagnetic force, right, with respect to each other. Okay. As because of this, interlocking is obtained, and as because of interlocking, we are able to define the frictional force, right? So it is an electromagnetic force, right, interlocking between the two contact surfaces. Now, suppose high value of the force is applied, right? What will be the direction of the frictional force? First, we define why. What is the reason behind? So the reason is it is an electromagnetic attraction between. The logic, interlocking. What will be its direction? Step to step. Suppose this is an object, high value of the force is applied, this is interlocking. If high value of the force is applied, in anyhow this interlocking will get braked. This interlocking will get braked, like this way. Okay. First it was like this, and now interlocking will get break and it will object will move like this way. Right. So in that case, right, what will happen? What will be the direction of friction? The direction of the friction, right, is decided in a way that we need to oppose the relative motion between two surfaces. Direction, again I'm repeating kindly, right, I'm highlighting that stuff, right? The direction of the friction is decided in such a way, right? The direction of the friction is decided in such a way, right, that we can stop, we can oppose, not stop, we can oppose, right, the relative motion between the two surfaces. Suppose this is M, it is moving like this way, na? Friction will oppose it, right? Friction will oppose the relative motion. Suppose it is moving like this way, na? Right? The friction will try to, right, this, right, what we can say, this the upper one, right? It will act into the backward direction for the upper one. Suppose this is M, right? Okay, and this is a surface. Okay, now suppose if you want to stop the relative motion between these two, right? Suppose you want to stop the relative motion between these two, then what we need to do, right? Okay, see, this is a friction is there, right? So friction will pull F into the backward direction and it will push surface into the forward direction. Then and then only the, right, okay, the relative motion between two object, the two contact surface will be opposed, right? Suppose if the particle is moving like this way, right, the friction will try to pull this upper particle, the upper object, into the backward direction and lower into the front direction. This is how the friction is opposing. So in all of these cases, if the direction of the friction is asked, then you always have to consider that it is to oppose the relative motion between the two contact surfaces. Now, let's move on to the formula and the graph. Right. Suppose this is a particle M, right? Okay. Frictional force is always equivalent to mu of N, right? Mu of N. This is a formula of friction, but there exist, right, many kinds of, right, lots of confusions are there in the mind of the students. So for that we are plotting up the graph of, right, frictional force versus applied force. Frictional force versus applied force. Suppose, first step, we are going to classify what is static friction, what is limiting friction, and what is kinetic friction. Static friction, limiting friction, kinetic friction. So let us take an example. If I'm giving the value as 2 kg, right? Okay, and we are taking, suppose, see, M, let us take an example. If we are taking M as 2 kg, right? If we are taking, right, m as 2 kg, right, and mu as 0.2, right, this two data suppose I am taking. What will be the maximum value of the force needed so that this particle can, right, so what will be the maximum value of the force needed so that that can be the relative motion between the two contact surfaces? That should be the relative motion between the two contact surfaces, right? So for that, first of all, I am going to calculate the limiting friction, right? FL, that is equal to mu of n, right? So that is 0.2 normal. This n is in upward direction, this is in mg in downward direction, right? To 0.2 into 2g, that is equal to 4 Newton. The value of the limiting friction is 4 Newton that we, right, calculated using the formula, the simple formula of friction. We calculated it, right? Now what is this value 4 Newton is? The name itself states limiting friction. The name itself states as limiting friction. Now what actual the limiting friction is? Right, the name itself states as limiting friction, the maximum value of the friction up to which interlocking will not get braked, the object will not start the motion. The maximum value of the friction, that is limiting. The name itself states in a limiting friction threshold value up to which the particle will not start. After this, interlocking will get braked and that object will start moving. What will happen beyond the limiting, before, what will be before the threshold value and after the threshold value? Suppose we got this thing. Suppose if 4 Newton is applied to this specific object now, right, okay, then he is going to, it will be on verge of moving. What will happen, the value less than 4 Newton, and what will happen, right, to the value greater than? Suppose first case, F is 1 Newton applied. Interlocking is a crazy phenomena. Limiting friction is 4 Newton. Before limiting friction, there exists static friction. Why it is named as static friction? Because in that entire phenomena is going on, object is not moving. That's why it is named as static. See, to move this object, 4 Newton is applied. 4 Newton is needed. To move this object, 4 Newton is needed. How much amount of the force we have applied? 1 Newton. 1 Newton is less than 4 Newton? Yes. Object is going to move? No. Why? Static friction is self-adjusting friction. Static friction is self-adjusting friction. According to the external force applied, static friction adjusts its value. Suppose if 1 Newton is applied, friction will adjust its value and will make 1 Newton. Suppose 0 Newton is there, friction is 0 Newton. Suppose 1 Newton is there, still object is not moving. Static friction will self-adjust itself and, right, increase its value to 1 Newton. Right? Okay, the graph will be like this way. Now this F is getting confused. Why object is not moving? So he thinks that let's increase the value of F. Suppose if I'm increasing the F to 2 Newton, again static friction will self-adjust and, right, it will try to save this interlocking. So if external forces applied is 2 Newton, right, static friction will, right, self-adjust to it. The graph will be straight line. Up to what limit the static friction will try to self-adjust? Now the external force applied is 4 Newton. right? Again the static friction will be 4 Newton, right? Okay, so suppose this is a 4 Newton, right? And this will be the 4 Newton, right? So this will try to self adjust up to this, right? Like this way. Now we have reached to the maximum value of the static friction. The maximum value of static friction is limiting. When applied force was 0, static was 0. When applied force was increased to 1, static self-adjusted and increased its value to 1. When applied force increases to 4, static friction try to self-adjust its values and increased it to 4. But now it has reached to the maximum value of the limiting. This reached to the maximum. Now if applied force is increasing its value, static friction is not going to do anything, right? It will be nothing will be in its hands, right? Because the external force values has reached to the value of the limiting friction. It means that, right? It means that, right, the object is on verge of moving. So at this point, object will be on verge of moving. So from this to the maximum value of the limiting friction, object is stationary, and that's why we are using mu s, that is known as coefficient of static friction. Now after this, suppose if I'm applying F as 10 Newton, whoa, interlocking will break. Why? Our limiting friction value is 4 Newton. But we have applied more than 4, that is 10. Interlocking will break. This section of the graph, right, shows the interlocking has gone. Why? Because we have applied the value of 10 Newton. And that external force, that value we have applied, it is the value of external force and it is greater than limiting friction. After this, suppose if I am applying, right, after this, now object is in moving. So whenever the object is moving, we are having the kinetic friction. So it means here the formula will be mu k of n. Always mu k value is less than mu s. Why? Because here in mu s interlocking is not getting break, but in mu k interlocking is getting break. That's why the graph is like this way. And after that, value of the friction will be constant till end, and that value will be kinetic friction. Right now, after that, if you are applying suppose 1000 Newton also, then like suppose if you are applying 1000 Newton, once it has crossed the limiting value, right, kinetic will be constant till infinite, right? Kinetic will be constant, right? So what the entire process tell? First we need to calculate the limiting. Suppose limiting is 4. Now external force applied is 0, static friction self-adjusted. Applied force is 1, static friction self-adjusted to 1 and save the interlocking. External force applied is 4. Now static friction has reached to the maximum value, that is its limiting value. Right now the object is on verge of moving. Now after that, suppose if Fx external force is increasing its value, then that static friction is not going to do anything. So after that, right, suppose if 10 Newton is applied and it has crossed the limiting value, interlocking will break. Now the static roll is ends here. Interlocking will get break. Okay, one jerk is obtained. This is jerk that shows the breaking of the interlocking jerk, right? And after that, here comes the role of the kinetic friction when the object is moving on rough surface, right? And after that, suppose if external applies, right, 1000 Newton, then also the kinetic friction is constant. So the graph is like this way, right? Graph is like this way. It starts from here right? It moves to here and it's like this way, right? So this is what an actual concept, and value of the kinetic friction is always less than coefficient of static friction. Mu is the coefficient of the kinetic and static friction, right, that you all are aware of. In some of the cases, right, this jerk is so negligible that mu s and mu k is considered as equal. In some cases jerk is negligible, then this both are considered as equal, else kinetic value never exceeds, right, okay, to the limit this static value. Okay, so this was an actual graph. Okay, now after that, okay, first of all let's see sums, right, related to this, and then we are going to solve, right, the sums of the right, two block systems we are going to solve. Okay, now see, a plank with a box on it, there is a plank with a box on it, it is gradually raised above the other end as angle of the inclination with the horizontal reaches 30 degree. The box starts to slip and it slide down 4 meter in 4 seconds. The coefficient and stri are will be, okay, coefficient of static and kinetic friction will be respectively, right? So in this case we need to calculate the both, right? In this case we need to calculate the both. It's a very simple thing, right? Suppose mg, okay, mass, okay, mass is given. Okay, the box start to slips and slide 4 meter down the plank in 4 seconds. The coefficient of the static and kinetic friction. Okay, first of all let's draw the FBD. Suppose this is mg, this is the value of n, right? This is mg, right, cos of theta, right? Okay, this is mg, right, sine of theta. This will be the value of the friction, that is equivalent to mu of n, right? Okay, this value will be equivalent to, right, mu of n, friction, that will be equivalent to mu of n, and this will be the direction of net acceleration. This question is asked into 2015 question in 2015, and it's really nice, right? So see, we draw down the right, okay, now what will be the value of the net acceleration? Mass is not given, right? So can I write it down? Net acceleration into the downward direction, that is ma of net acceleration. Net acceleration is in downward direction, na, right? Okay, so as I said before, whenever we are dealing with an inclined plane, always consider the inclined plane surface as a x-axis and perpendicular to it as a y-axis, right? So it is in the downward direction, right? Okay, so this will be the higher and the friction will be the lower magnitude. So it's mg sine of theta minus mu of n, right? It's mu k of n, because object is moving, that's why we have kept it as a kinetic friction, right? Object is moving, that's why we have kept it as a kinetic friction. So m will get cancelled, so a net, that will be equivalent to g of sine theta minus mu g, this will be mu k g cos of theta, right? Can I consider this as equation number 1? Yes. Now, as I said before, when the object is stationary on the surface, there exists an interlocking, right? So at that position of the time, we are having the coefficient of static friction, right? But in this case, we will be having the right coefficient of the kinetic friction. Okay. So whatever the values we are getting from the coefficient of kinetic friction, and after that we'll show you the coefficient of static. Okay, now see, a net is equal to g sine theta minus mu g cos of theta. Okay, now in 4 seconds it is traveling 4 meter. In 4 seconds it is traveling 4 meter. So it means that suppose from position A, u is 0, it is reaching to position B, it is moving down with the net acceleration. 4 meter distance is traveled into the 4 seconds of time interval. Acceleration is constant. Can I write it as SC is equal to u of t plus half at square? From here, the net acceleration we are getting it as 0.5 meter per second square. Right? Can I replace this value here, right? So it will be point of phi is equal to g sine of 30 minus mu of k g cos of 30, right? So it's phi, point phi is equal to g by 2 minus mu of k g root 3 by 2. Okay, so it will be 1 is equal to g minus mu k g root 3, making g is common, right? So 1 is equal to g 1 minus mu k root 3, right? So 0.1 is equal to 1 minus mu of k root of 3, right? So mu of k root of 3, that is equal to 0.9. So mu k, that is equal to 0.9 whole divided by root 3, right? 0.9 whole divided by root 3. So this is the value of the coefficient of the kinetic friction, right? Okay, this is the value of the coefficient of the kinetic friction, right? Okay, we are going to obtain it here. Okay, don't get worried. First of all, we are going to we completed the entire procedure, just the final evaluation is remaining. Now, what about coefficient of the static friction when the object is stationary? Then when interlocking is there, right? So it means that when the object was about to slide for very small amount of the time, there exists the, right, there was a presence of static friction. It means that when we need to keep, right, the object as rest, then we can calculate the, right, concept of the, then we can calculate the value of the coefficient of static friction, right? So at this point of time, if net acceleration is getting 0, friction and mg sine theta will get balanced, will get the value of the coefficient. Because the object is stationary, na, what will be the value of the friction? Mu of n, that is equal to mg sine of 30, right? Mu of n, that is equivalent to, right, mu of n, that is equivalent to mg sine of theta 30, right? What I have to write here? It should be mu s or mu k. It should be mu s. Why? Net acceleration is 0, object is stationary, and whenever the object is stationary, we are having static friction, right? So here mu s mg cos of theta, that is mg sine of theta. mg is going to cancel. Mu s, that is equivalent to tan of theta. So mu s, that is equal to 1 by root 3. This is the value of the coefficient of the static friction, right? This is the value of the coefficient of the static friction, right? And this is the value of the coefficient of the kinetic friction. Now we need to evaluate this, right? We need to evaluate, right, this part.
So the value for this static friction, it is equivalent to, right, 0.6, okay, and this one will be approximately equivalent to 0.5, okay. So I think the D is the perfect answer for this specific question, right? Okay, now let's move on to the next. See, a system consists of 3 masses m1, m2 and m3 connected by a string passing over a pulley P. The mass m1 hangs freely and m2 and m3 are on the rough horizontal surface. The situation is like that, right? This is a rough horizontal surface with a coefficient of the friction mu, right? Okay, this is a pulley connected. I'm sorry, right? This is a pulley connected, right? Here m2 is connected, and with m2, right, m3 is connected, and m1 is hanging freely. Situation is like this way. What we need to calculate? We need to calculate the downward acceleration of the masses, right? Downward acceleration of the masses. It's very simple stuff. Okay, can I say that the formula for the net acceleration? See, suppose if it is moving into the downward direction, then it will be the net acceleration. Then these 2 blocks will move into the left direction. Suppose if m2 and m3 are moving towards the left direction, right, the relative motion is like this way, so friction will try to stop it, so it will act into the opposite direction, right? So this will be mu m2g and this will be mu m3g.
What will be the formula of net acceleration? That will be net force whole divided by masses of system. Right. All of those tensions are getting cancelled. Suppose here we are having T. Okay. Then here we are having T. Suppose here we are having T1. Here we are having T1. Right. So what will be the net acceleration? T minus T plus T1 minus T1. Right. Plus. Right. Weight that is acting into the downward direction, that is m1g, minus, these are the opposing forces, okay, m2g minus mu m3g whole divided by mass of system m1, m2, m3. Now all of those masses are equal as mentioned, right? m1 is equivalent to m2 is equivalent to m3, right? Okay, now so the net acceleration of the system in this case will be, see, all of those tensions will get cancelled, right? So it is okay, m will also get cancelled, right? So I think finally we are having it as a, right, 1 minus 2 mu g whole divided by 3. This is a net acceleration of the system with which m1 is moving into the downward direction. Okay, so the C will be the perfect answer for this specific question. C will be the perfect answer. Okay, now let's move on to the next part. A block B is pushed momentarily along the horizontal surface with an initial velocity v. If m is the coefficient of sliding friction between B and the surface, then block B will come to the rest after what time? Initially it is moving with the velocity v. After some time the velocity of the block is getting completely zero. The velocity of the block is getting completely zero. It means some, right, a retardation is present that is opposing the motion of an object and decreasing its velocity. You can see the velocity is in this direction, acceleration is in opposite direction. It means acceleration is opposing the motion of an object. In another sense, it is retardation, right? So here it's very simple. This retardation is provided by the rough surface. So guys, just keep one thing into your mind. Whenever the retardation is provided by the rough surface, it means by friction, then that value is always equivalent to negative of mu g, right? That value is always equivalent to negative of mu g. You all are aware of this stuff, right? So this is constant, right? So let's apply the equation of the motion in this case, right? Let's apply the equation of motion in this case. So we will have v is equal to u, right, minus mu g t. Final velocity will be 0, u minus mu g of t, right? This is v. So time to stop will be v by mu g. And this will be the perfect answer for this specific question, D. Right? Okay. Okay. Apart from this, right, this question I've given you all into the homework, but we can solve it. Let's solve this stuff. The coefficient of the static friction mu s between block A. Okay. This is mass 2 kg. Coefficient of the right static friction is value is 0.2. Right. System is like this way. Okay. Now, what would be the maximum value of the mass of block B? So that what will be the maximum value of the mass of B so that both blocks should not move, right? Do not move. See, if it is written, it is mentioned into the question that both blocks do not move, it means that net acceleration of the system is 0. The downward acceleration of the A is 0, right? The right side acceleration A is 0. It means all of the forces are balanced, right? All of the forces, they are balanced, right? So here tension is in upward direction, right? Weight of B is in downward direction. Tension will be in this direction and it is balanced by the frictional force. So here tension is balancing the weight of MB. Same string is connected to A. So that same tension is balancing the friction. So in another sense, if tension is balancing the friction, right? If tension is balancing the MBG, in another sense, friction should balance MB, the weight of the B, right? Now what is the friction? Mu, right, into 2g, that is equal to mb into g. G will get cancelled. Value of the mu is 0.2 into, that is equivalent to mass of b. So mass of b, that is equal to 0.4 of, right, kg. If this much amount of the mass is given to the b, the system will not move. See, actually the acceleration 0, it means there are two ways. Net acceleration 0, it doesn't mean system will not move. There is a possibility, right, that it can move with a constant velocity because forces are balanced, right? Net acceleration is having the two sense. Okay, net acceleration is equivalent to 0. It is having the two senses, right? One, velocity is 0, right? Second, velocity is constant. So if you are putting 0.4 kg, then there is a possibility that system can move with the constant velocity. But more than that, system will get stopped. Okay, so the D will be the perfect answer for this specific question. Right. So guys, this is a homework, right, question from my side. You can answer this homework question beneath the video, right? Okay, even this is also the homework. Very nice sum to calculate the friction, right? Okay, this is also from my side. Okay, and let's move on to the two block system now. We are going to see only two sums of the two block system, but really we are going to, right, grab that thing into the mind. Two block systems, right? The next 10 minutes to do this systems, right? And we are going to stab it. Okay, see, suppose this is a surface, right, where coefficient of the friction is completely 0. This is a 3 kg mass, right? This is a 4 kg mass. Here coefficient of friction is 0.3. What will happen? What will happen? Suppose if F is applied to the lower block, what will happen? If F is applied to the lower block and value is quite high, the lower block will move into the forward direction and the upper one will move towards in the backward direction. The lower block will move into the forward direction and upward will move into the backward direction. Is it true? Yes, obviously it is true. But here we haven't defined the value of F. At what value of F this will happen? At what value of F this will happen? That's an important step, right? Lots of questions we are having. At what value of the F the system will start moving? At what value of the F they both will move together, right? Because the possibility is that the force is applied to the lowermost object. So there is a, what we can say, there is a possibility it may move into the forward direction and 3 kg can move, it can be pushed backward. We don't want to do that. We want that value of F, right, up to which these two blocks can move together like this way with a common acceleration, right? So let's draw the FBD for it. Okay, this is the 3 kg, right, and this is a force applied. As I said right into the beginning of this, the concept of the frictional force, as I said, it's very, very simple. Friction means to oppose the relative motion of the two contact surfaces. At the bottom level, friction is not there, means the system is going to slide, that is fixed. So whatever it will go on in between 3 kg to 4 kg, right? Possibility of a relative motion that can occur in between these two blocks is like this way. 4 will move into the forward direction, 3 will move into the backward direction, right? So in this case, friction will try to oppose this relative motion. So for that, friction will force, right, 4 kg, it will pull 4 kg into the backward direction and it will push, right, 3 kg into the forward direction. The force is like this way. Friction for 4 kg block will act like this way, right? Okay, this direction of friction can only oppose the relative motion between the two contact surfaces. This is what friction is all about, to stop the relative motion between the two contact surfaces. Both are having the common acceleration A. because we want that value of F, right? Okay, up to which they both will move together. First of all, let's use this 3A, that is equal to friction. So 3A, that is equal to mu. Now what is the normal? And here it is in upward direction, and this will be equivalent to 3G, right? And the bottommost, right, and 2, it is 3G plus 4G. At the bottommost surface, we are having the weight of the whole system. So that's why at the bottommost part, we are having the reaction as 3G plus 4G. And in between these two blocks, we are having the reaction of 3G, because only the load, the weight of the 3 kg is applied on it, on this contact surface, right? How much load you are applying on the contact surface, the amount of the reaction it will produce. Similarly, 3 kg is applying 3G amount of the weight on that contact surface. So we are having the reaction of 3G. Similarly, at the bottommost part, the entire system is, right, applying the load. So we are having the, right, 7G as a normal. Here it will be mu into 3G, right? So acceleration will be 3 meter per second square. This can be the common acceleration of the system, right? Now, what will be the value of the force, right? So can I say 4A, that is equal to F minus 9. So F will be 12 plus 9. F will be, that will be equivalent to 21 Newton, right? F will be equivalent to what we got. We got the maximum value of the F. See, I'm writing the 3 criteria here. First, if F is less than 21 Newton. Suppose, see, external force completely depends on us. In this kind of the sums, first of all, we need to check, right, the threshold value. Then how much amount of, at what value of F both will get separated. This we need to check, because by doing so, right, okay, it is really going to help the sums to solve the sums easily. If F is less than 21, right, F is less than 21, okay, both will move together with the common acceleration. Right, if F, that is equivalent to 21 Newton, the both blocks are on verge to get separated. And third, if F is greater than 21, they will be separated with the different accelerations A1, right, and A2. They both will get separated with the different accelerations A1 and. So less than 20, this is 21 is our threshold value. Less than that, they both will move together with the constant acceleration. That is, it's not a big deal, right? Okay. More than that, they will get separated. At 21, they are about to get separated like this way. The moment before separation start, just a moment before the separation start, that is the moment of F is equal to 21 Newton. Now suppose same example we are taking, 3 kg, 4 kg, mu is equal to 0.3. Now this time I'm taking the friction at the bottommost part also as 0.2. Now how much amount of the F is needed? How much amount of the F that is needed, right? How much amount of the F it is needed? Simple. Half of this sum we have already done. Okay, let's draw the FBD. Okay, this is a 3 kg, right? This is a 4 kg. F is acting into this direction. Similarly, the friction 1, right? Both are having the common acceleration, right? Now there is another friction. In previous question, if I'm talking about, right, the coefficient of the friction at the bottom of the bottommost part, right, bottommost surface was completely, right, it was not rough, it was smooth.
The system was easily sliding on that. The lowermost block was easily sliding on that. But in this case, we are having the friction. It means that for entire system, we are having the another value of the friction, that is FR2. In previous case, F was applied in such a way that they both shouldn't get separated. We got the maximum value of the F. In this case, first F need to think about to overcome this value of the FR2, then system will move, and on the third step, blocks will get separated. In previous question, on very first step, if you are applying less than 21 Newton, they both will move together. Right? If you are applying greater than 21 Newton, they both will get separated. Only two priorities were there. Here we are having three priorities. First of all, we need to overcome the friction of a ground on which the entire system is placed. Then we have to move on to the next step. What will be the value of F? Right? They both, for that value, they both should move together. Right? So in this case, see. Again, 3A, that is equal to value of friction 1. A is again 3 meter per second square. We are getting the common acceleration as 3 meter per second square. Now this time 4A, that will be equivalent to F minus friction of 1, right, plus friction of 2. So F will be 12 plus friction of 1 plus friction of 2. Friction of 1 you all are completely aware of, right? N1 in this direction, the load applied, that is equal to 3G, right? So the friction of 1 will be 12 plus mu. Mu is 0.2 into 3G. Plus, what about this friction at the bottommost surface? See, I'm talking about the contact surface between the 3 kg and 4 kg of the particle. So in between that, right, okay, only 3 kg load is applied. So for that, we are having the reaction of 3G. But if I'm talking about the bottommost surface, 3G plus 4G, 7G of the load is applied, and for this, at this bottommost, right, we are having the normal, right, of 7G. And what is the friction value point? Here we are having 0.3, and this will be 0.2 into 7G. So here it will be 12 plus 9 plus 14, right? So this will be 35 Newton. In the previous question, we got the value of F as 21 Newton. Why that was less? Because at the bottommost part, friction was not present. But in this case, we got the value as 35 Newton. Now let's understand this final stuff first. If 0 is less than F, what is the value of the FR2? That is 14 Newton. If F applied is between 0 to 14, right? If it is between 0 to 14, right? Then what will happen? It's a very simple thing. Okay, system will not move. Entire system will not move. If system is not moving, right, how we are going to identify whether the blocks will get separated or not? If system is not moving, then how we are going to identify whether the blocks will get separated or not? So F is greater than 14, system will move. Second, in between 14 to 35, right, both blocks will move together with the common acceleration, right? F greater than 35, equivalent to 35, they will be on verge of moving, right? They will be separated with a different acceleration, A1 and A2. right? They both will get separated with the different accelerations A1 and A2, right? So this is what the difference between the two questions is, right? Okay. So now, I think this was up to the friction part. Okay, this was up to the friction part. Okay, and see, apart from this two friction, we are having another two theories, right? See, motion on the banked road and the motion on the bank curve road. It's a very simple thing. It's a direct formula. Suppose if a car, right, want to takes an effective turn, right, on a road where, right, the curvature of the road is, right, R. Okay, the curvature of the road is R. Suppose if this car wants to take an effective turn, suppose this car want to takes an effective turn, then we are having the direct formula for this V, that is equal to under root of mu s rg, right? Because the necessary centripetal, right, is provided to move on the circular path. Obviously the centripetal is needed, right, and that necessary centripetal is provided by the friction, right? So mv square by r, that is equal to mu mg. From this we got this equation, so it's not a big deal. This is the direct, from this we are having the direct formula based question, right? Even from the right questions of the death well, right? Okay, suppose a car is moving at this part, right? Okay, this is a death well, right? Okay, now in this case, okay, suppose centripetal is acting in inside direction, normal will be n cos theta, right, and it will be n sin theta. Similarly, friction will act into the downward direction. For this we are having the two components of the friction, right? This will be fr sin theta, right, and mg will also be in downward direction, right, and this will be fr cos theta, right? So this is for a car, right? So as summation of the all x forces is 0, summation of all f right, y forces is 0. In simple terms, right here, mv square by r, that will be equivalent to n sine of theta plus friction of cos of theta, right? Similarly, okay, this one, okay, n cos of theta, that will be equivalent to, if I'm talking about the vertical forces, fr sin theta. Can I consider this is equation number 1, this is equation number 2? Solving 1 and 2, we are getting velocity maximum as rg 1 minus mu, I'm sorry, right, mu minus tan theta, mu plus 1 minus mu tan theta, right, whole to the power half. Okay, this is a direct formula based question, right? Not a big deal to solve, you all are aware of it, right? So this much from my side for the motion, for the friction. Now let's move on to the next concept of the, right, pseudo force. We have to apply the direct formula. Now let's move on. See, now two part of this chapters are remaining. One, that is a pseudo force, and second, that is a spring force, right? Spring force we are going to cover, right, with the work energy and power, and maximum use of the springs are in that chapter only, right? Maximum use of the springs, right? Spring force, right, we are not going to explain in this session, we're going to explain into the next part. Okay, now let's move on to the concept of the pseudo force. Very simple, in short, into the summarized form I'm going to explain. I'm going to show you some examples. Pseudo force, first of all, I want to tell you that pseudo force, it is the kind of the fictitious force. It is a fictitious force. This force never exists. First of all, the most important point about the Newton's law of motion is that Newton's law of motion are only applicable right, the Newton's law of motion are only applicable, right, okay, in inertial frame. Inertial frame with what? Inertial frame, right, okay. Inertial frame means what?
The Newton's law of motion are only applicable into the inertial frame. Inertial frame means frame velocity is constant or object is on the ground. When, right, frame is non-inertial, frame is non-inertial, Newton's law of motion fails. For that reason, to use the Newton's law of motion in a non-inertial frame of reference, pseudo force is needed. To use the Newton's law of motion into the non-inertial frame of reference, pseudo force is needed. How? Let us take a very simple example. One observer is standing on ground. Right? It means it is an inertial frame. He saw a lift that is getting accelerated into the upward direction. Mass is hanging inside the lift, right? And for that, tension is in upward direction. If I'm using the inertial law, Newton's law of motion into the inertial frame, obviously it is a very simple thing. Right, net acceleration is in upward direction, right? Okay, in the direction of the net acceleration, t is of the higher magnitude minus lower magnitude. So what is the equation of the tension I'm getting? That is ma plus mg, right? That is actually a correct equation. That is actually a correct equation. But what will happen? See, from ground, if I'm analyzing the situation, lift is moving up. True. But when I'm analyzing the same situation, right, inside the lift that is accelerating upward, mg will be in downward direction, tension will be the upward direction. When I was analyzing from the inertial frame, right, object was getting accelerated. But when I moved on to the non-inertial frame, inside the lift, now block appears stationary to me. So in that case, if I apply the Newton's law, T is equal to mg, that is wrong. Why this equation we are getting? Because the observer is also getting accelerated with object. And relative acceleration between them two is 0. We are not getting this equation because this is a non-inertial frame. Observer is inside the accelerating lift. For that reason, pseudo force is needed. Now, first point. Acceleration of frame is applied in opposite direction to an object. How pseudo force is applied? Pseudo, mass of object, acceleration of frame. This is an actual right formula of the pseudo force. Acceleration of the frame, it is applied into the reverse direction. If you are in non-inertial frame, what you need to do? See, suppose same example I am taking, right? Observer is inside. mg is acting into the downward direction. This is t. Frame, it is getting accelerated. What we need to do? We need to apply, right, the acceleration of the frame in reverse direction to the object. Now, if you are observing, see, the right equation is coming out. You can compare this to examples. The right equation is coming out. Right? The right equation is coming out. So as because of this reasons, right, pseudo force is, right, the existence of pseudo force came, right, that to use the Newton's law of motion into the non-inertial frame. Right? Apart from this, okay, let's have some examples related to it. Okay, it's a very simple thing. It's not a big deal, right? Pseudo force is a very simple thing, right? It's not a big deal. Okay, now suppose right, okay, this is a frame, right? Observer is inside the frame. Suppose this frame is getting accelerated with A and there is a presence of inside the balloon. At what angle it will get tilted? With respect to vertical at what angle with respect to vertical it will get tilted, right? Observer is inside the frame, then obviously, right, reality is not going to. So what we need to do, we need to apply the acceleration of the frame into the reverse direction. So what actually it will happen, with respect to vertical, theta will be like this way, and this will be the pseudo force, right? mg is acting into the downward direction. Tension is like this way, this will be the t cos theta, right? And this will be t sin theta. Now what will happen if acceleration is applied to the frame, right? This ball that has been hanged, it will move aside, right, at some angle, right? And it will get stuck at this position like this way. Suppose if I'm standing into the frame and frame is, suppose I'm standing into the room, right, and so room is getting suddenly accelerated into the forward direction, then I will feel a jerk into the backward, right? An observer who is present inside the room, who is analyzing the situation, right, then if he needs to apply the, right, Newton's law, then he need to apply the pseudo force into the backward direction. And suppose if I'm getting jerked like this, suppose if I'm moving into the right, the car is moving at a very high speed, what I feel like the same thing is ball is stage. At this point of time, the equilibrium will be attained. So t sine of theta, that is mass into object into the acceleration of the frame, t cos of theta, that is equal to m of g, right? From this we are getting a is equal to g of tan theta, right? So this is what, and the actual concept, this is the first sum of the pseudo force, right? If you want to have a snap, you can just have a snap it, right? Okay, I'm giving you on the countdown of 5, 4, 3, 2, 1. Now suppose the second example, there is one cart, there is one cart, a block is attached to the cart and this much part is rough, right? This much part is rough, small m. How much acceleration we need to provide to the cart? How much acceleration should be provided to cart so that m should not fall? This shouldn't fall down, or this shouldn't slide down. How to solve this? Very simple. Where is the observer? Observer is on the accelerated frame. Observer is on the accelerated frame. Now what we need to do, right? Very simple step. We need to apply the, we need to draw the FBD for the small m, right? What will be the value of the C? mg is acting into the downward direction, right? If the relative motion is like this way, then friction will try to oppose it, so it will act into the upward direction, right? Now acceleration of the frame into mass of the object, so pseudo force will be like this way, mass of the object into the acceleration of the frame, and if pseudo force is applied in this way, then it will create the enormous amount of the normal, right? So that it will create the, see, if pseudo force is applied into the reverse direction, then obviously the contact between these two surfaces will get increased, right? And that will result in increase into the value of the normal reaction, right? Now we want to keep this system as stationary. They should not fall down, right? So can I say N, that is equal to MA, equation number 1, right? Friction, that is equal to mg, and that is equal to mu of N. So mg, that is equal to mu of m into a. Mm will get cancelled. Mu is equal to g by a. Right, n will be equivalent to ma. Mu of n, that will be equivalent to mg. So mg, that will be equivalent to mu of ma. Right, so the coefficient of friction will be mu g, and a will be, right, g by mu. This is the maximum acceleration you can provide, right? Okay, below this it will slide down. Sorry, minimum acceleration, right? Okay, so this is what an actual concept of the pseudo forces, right? Okay, so now from the beginning, okay, of the session, let's move on, right, to what we have seen and what we, okay, I think right, okay, we have moved apart. Lots of things we have seen in this lecture. Okay, if we moved on to the flow chart, let's have the final glimpse, right? Okay, and the spring force that is remaining, that we are going to conduct, we are going to see into the work energy and power, the separate session in which we will conduct, we'll see what is the springs in series and parallel, lots of things we are going to discuss, right, in the work energy theorem also, right? See, after that we moved on to the this Newton's first law. We saw the inertia, Newton's second law, impulse, conservation of linear momentum, some of the examples related to it. And after that we moved on, right, I'll give you the homework, the third law, Newton's third law, types of forces, normal reaction, right? And after that we moved on to the tension, the massless ropes and the ropes with masses m, right? And after that we moved on with the, right, the constraint problems and some of the problems related to the tension. And then we moved on to the constraint relations, 3 shortcuts we saw, right? 3 shortcuts we saw, right? And finally after the constraints, right, this is a wedge constraint, and after constraint we moved on to the frictional forces, relative block problems and everything, right? Some of the examples we saw, and finally we saw the, right, concepts of the pseudo forces, right? Some of the homework questions I gave, right? Okay, bank curve road and banked road we saw, right? And after that, sorry for this error that we got into the friction, right? Okay, and after that we moved on to the concepts of the pseudo force, right? Okay, and finally, right, okay, this thing is there, and spring force that we are going to conduct into the next part, right? Even this lecture is quite long also, right? Thank you. So guys, it's time to go again. I will come back with a new lecture of work energy and power, right? So this is Indrajeet Singh. Hope so you like this lecture of whatever the content we gave, and thanks a lot for the time and the cooperation that you gave by watching this teaser, and thanks for the love that you showered into the comment box, right? So guys, please support us, right? Please support our entire team, because without you we are nothing. I want you all to be right, stay tuned to this channel, watch all of those lectures, those who are uploaders that we are uploading, right? Because it's for you all. If you are not going to give us the response, then, right, all over this efforts will be in vain, right? So please guys, right, I will be waiting for all of your comments beneath the video about this session, right? So guys, it's time to go. Okay, so this is Indrajeet Singh signing off from the desk, right? Bye bye, Sat Sri Akal and Namaste from my side, Bachaji. Bye everyone, stay at home, stay safe, stay healthy. Thank you. Bye in amidst the pandemic. Bye everyone.